Yes, sir.
Yeah. Shall I start?
Yes, please, sir.
So last class, so I think Anish, you were there in the last class. Vijayalakshmi, you were also there in the last class, isn't it?
Yes, sir.
So we started with some of the history of anesthesia, how early anesthesia was administered, especially GA by the open drop method, what were the instruments used, and who are all contributed to the development of anesthesia machine from the scratch, from the simplest form to the various improvements that were done in the anesthesia machine. Year-wise, we saw how the flow meter was added, how the vaporizers were added, and what are all the agents that were improved and then shared. So like that, the machine became more and more improved. And the current version of workstation, which all of you are now currently using, they incorporate both electrical and pneumatic components to operate the machine. Whereas earlier machines were purely operated by the gases, the pressure delivered by the gases, which is called the pneumatic component. Okay. So we saw various parts of the anesthesia machine, and the common questions they will ask you in the practical examination. We saw all those pictures and then we made it into a question answer type. Now, to complete the description of the machine, we will now go over to the machine, and when we describe the pneumatic component, how can you classify the machines components based on the pressure? Have you all read about that? What are the various segments based on the pressure?
Intermediate, low pressure, sir.
We have high pressure segment, we have intermediate pressure, and we have low pressure segment. Okay. So that is how even today, even your workstation is operating. So based on the pneumatic component, we have to understand which are all the components which come under the category of high pressure, which are all the components which come under the category of intermediate pressure, and which are all the components which come under low pressure system. So with that, I will just go to share the screen, and so all of you may be remembering this is the history part which we saw. We saw about the Morton and his inhaler, the ether dome, the first demonstration of ether anesthesia, all those things we saw. Then we saw the oldest type of equipment used for open drop method, the so-called the Simmel-Busch mask, and the bottle that was used to drop or pour ether onto the mask was called the Bellamy-Gardner ether dropper, and modification for providing oxygen also through this nipple and then multiple holes to deliver the oxygen so that the patient does not become hypoxemic. Because in open drop ether, it is the atmospheric air which vaporizes the liquid agent, ether. And then patient gets only 21% oxygen, unlike the present day where we give more than 21%, we give minimum 30% or 25%. So to give additional oxygen, they improved this. And this was the old method of giving anesthesia, with the flow meters were incorporated. And these vaporizers, which are called the Boyle's bottle, were having no sophistication. Their concentration was not calibrated. They did not have temperature compensation, and they were not very precise. They were giving a slightly improved version of the open drop. And this machine had a switch which can switch over from controlled ventilation to spontaneous ventilation. And once you switch over to controlled ventilation, this trilene lock or trilene lever cannot be operated. So they called it as trilene lock or switch circuit selector is the name for this particular component. And then this is the person who developed the Boyle's machine, and this was the oldest prototype of the machine which was developed. And then the type of wheels fitted to the old machines, even the now present day machines also have that's called the caster wheels. And then we started describing the machine from the earliest version, and slowly how it improved, what are all the components that were added to that, we are all included. And this is the modern anesthesia workstation, which most of you are familiar with, and you are using it day in and day out. And what are all the features incorporated in that we discussed. And we saw about the source of the gases, how it was delivered from big cylinders stacked in a room called the manifold room, which is far away from the areas of delivery of gases. But it had a reserve bank and a bank in use, and then the correct method of storing the cylinders and transporting the cylinders, and how the panel automatically switches over from one bank to another when the bank becomes empty, and how you have to replace that. And the source of oxygen, especially for a very large hospital requiring large volumes of oxygen. We discussed about the liquid oxygen plant, what is the physical features like the temperature, the pressure inside, and what is the current method of getting oxygen, that is called the pressure swing absorption, where the oxygen is made from the ambient air itself without depending on other sources. So we have such advancement in the development of oxygen delivery. And the medical gas pipeline, when it is supplied from a central source, how the pipeline should be laid. That also we saw, like main pipeline, risers and branch line, and where all the alarms should be placed to show whether there is enough pressure in the gas line or whether there is dropping, and how to install those pipeline and what are all the problems in setting up the pipeline. This asked as a question in sometimes in the theory also. So I prepared that. And then these are all the panels which you will be seeing in your OTs to show the pipeline pressure from the central supply, as well as the shut-off valves, which should be present in every area for local repair or replacement of the worn-out parts in the pipeline. So you should have facility to stop the gas flow. And this is the common question of asking about the cracking the cylinders before fixing them, especially the portable compressed gas cylinders should be slowly opened to remove any oil or dust particle at the outlet of the cylinder, so that there is no fear of fire or explosion. So it is called the cracking of cylinder. So you open the cylinder and close it and then fix it. And then this is the modern anesthesia machine, where we see this is the back side. All of you will be familiar with. If you go and see the back side, you have electrical outlet connections. Plug points will be there to connect your monitors and other equipments which require electrical power. And these are all the computer ports which can be attached, and then you can collect the data from the machine and store it in a central area for future analysis. And this is how the panel will show the pressure in the outside. So this is the safety feature, and alarms will be making a noise if there is a drop in pressure. And this is the multi-parameter monitors which are usually attached to your anesthesia machine, as well as the ventilator monitors. And this is another back look of your present day anesthesia machine. These are all the computer points ports or data ports as they are called. And we saw about the how to trace the path of the gases from the source, then to the high pressure regulator, then to the oxygen failure devices, and then the flow meter, and then vaporizer, and then finally to the common gas outlets going to the breathing system. So step by step, I showed all these things. And what is the importance of having a ambu bag in the theater in case of failure of oxygen supply or other gas supply? You can always detach the patient from the anesthesia machine and ventilate him with ambu bag. So the basic principle is ventilate and oxygenate and then troubleshoot later. And then we saw how the gases from the central pipeline are all delivered at the various outlets. The old method of wall outlets, then the ceiling pendant, the quick connector which are present in the modern theaters, and the probe that is going there with a diameter collar which prevents one force being connected to a wrong outlet. Then we saw all the pressure gauges both for cylinders as well as pipeline. Then we saw about the valve portion of the cylinders, the various parts of the cylinder, the color coding, and the various types of cylinders named in the alphabetical order, their fire pressures, and then the capacity. And then we saw about the application of Boyle's law, etc. And then the label which is there in the all the cylinders, what are all the information that you get from that. And then we saw about the place where we mount the cylinders, compressed gas cylinder, which is called the hanger yoke or hanger yoke assembly. And we saw what are all the parts. Again, we will be discussing superficially about this. And then we saw about the various keys which are required to open the cylinders, various types. And this picture you have to remember because these instruments may be kept in the Viva exam for you to identify. And always the opening is in the anti-clockwise and closing is in the clockwise for all the cylinders as well as vaporizers. And the importance of the Bodak seal to prevent leaking of the gases when it is fixed to the hanger yoke. And then we saw about the pin index system, which is a safety mechanism to prevent mounting a wrong cylinder in the wrong yoke. And then we saw about the modern machine having a APL valve, airway pressure gauge, and the switch to flip from manual to ventilator. And then this is the pressure regulator with the pressure gauge. This is the high pressure system which we will be seeing today. And the principle on which the pressure gauge works, which is called the Borden principle. And the person who designed that, Eugene Borden, and all these we saw. And it is based on a small toy, which is called the party horn, which straightens out when you blow. So that is the principle on which the Borden gauge works. And what are all the safety features on the pressure gauges we saw, how to calculate what is the definition of medical air and how much concentration of oxygen you will get when you get medical air, that the formula we saw. And also we discussed about the adiabatic changes which are likely to cause a fire and explosion, because when gas is compressed and released, there is energy released, and that may cause an increase in temperature and be the cause for fire and explosion. And we saw also about the Joule-Thomson effect, where the heat loss will happen when compressed gas is released suddenly to the atmosphere, and that will cool the water vapor in the surrounding atmospheric air, and that will form droplets or islets in the cylinder. That happens in the nitrous oxide cylinder, where the nitrous oxide is stored as a liquid and not as a gas. So up to this we saw in the last class. So today we will go to the next part. We start with the question: what are the safety features on the downstream of the back bar? That is, anesthesia machine has got a frame where there is a long rod going on the back side. That is called the back bar. Of course, now the modern workstations, it is all fully covered. It is like a wall. It is not like a bar. Whereas in the earlier machines, it was like a bar. Now, can you name some of the features that are there on the back bar? I'll start with one answer. There are oxygen failure warning devices which are powered by the oxygen pressure and the machine piping and activated when pressure decreases below 200 kilopascal. And in case of complete oxygen failure, ventilation with room air can be facilitated. So all this, this is one of the important safety features that is present in the downstream or in the back bar. Can you just name anything else? Anything about the vaporizers, the modern machine?
So vaporizer
Can you-
interlock system
Interlocking system. So
and
this
then
is how
proper
this
mounting
pressure
mechanism.
device works. And there is a spring-loaded non-return valve. Prevents surges back of the pressure, damaging the vaporizer and flow meter. This is downstream after the vaporizer, it will be there. Okay? So this is the spring-loaded non-return valve. And there is always a pressure release valve which will release the pressure if the pipeline pressure increases, that the back bar pressure increases more than 40. So this is the APL valve which you may not find in the newer machine, but this has been present in the older machine, but you must be aware of it because such machines will be kept in the practical exam for you to identify. And if they show you this, you have to say it is a pressure relief valve. And there is an emergency oxygen flush in the older machine, but this is the way it is present in the newer machines. Okay, so this is a comparison which I showed in the last class. The older Boyle's machine, which are pneumatically operated, no electrical component, this part which you see as a flap, there it is written off position. If this knob is on the upper side, there is no oxygen flush working. When you turn this knob downward, it will activate the oxygen flush. So this is the apparatus and this is the circuit selector. This is the common gas outlet. And you can see there is a separate pipeline coming to supply oxygen for the oxygen flush. So this steel tube, are you all able to see that? My pointer going on that?
Yes, sir.
Okay. So this is how the oxygen is delivered and you have to flip this switch or the flap downward and it indicates that if it is in the up position, it is in off. So when you switch it down, it will show on position and gas will rush through this common gas outlet. And the common question the examiners ask you is, how many liters of oxygen will be delivered if you activate the oxygen flush? Normally, we decide the flow meter. When we open the flow meter, we can give maximum up to 15 liters, isn't it? But when you activate the oxygen flush, how many liters of oxygen you can give?
35 to 70.
35 to 70, very good. 35 to 70 liters of oxygen per minute will be flowing, okay? What are the indications for using the oxygen flush? When will you use oxygen flush? This has been there right from the time the machine was designed.
And clear the circuit, sir. To clear the
Clear
circuit,
the circuit, yes. When do you want to clear the circuit?
to wash off the
Wash off what?
anesthetic gases.
In which condition you want to do that?
When you want the patient to wake up early,
Thick gases, if it is connected to the patient and you activate it, what can happen?
Barotrauma can happen.
Then will you do it if you want the patient to wake up early? Your answer was right. You want to wash out the anesthetic agent, but you must disconnect the circuit from the patient and then wash out. In which condition you will do that? Which condition can trigger high temperature in the patient, rigidity,
Malignant
and
hypothermia.
malignant hyperthermia? Okay, if in case you suspect malignant hyperthermia, you can disconnect the patient from the machine and then remove all the anesthetic agent that may be present in the breathing circuit by activating this oxygen flush. Okay. Now, earlier days, it was used as an emergency resuscitation method. When the patient is in hypoxemia, they advocated that you use oxygen under oxygen flush with 35 to 70 liters of oxygen so that you can control or remove the hypoxemia. But that is not used nowadays. So the only indication for using oxygen flush in the current day procedure is to remove the gases from the breathing circuit in cases of malignant hypothermia. Otherwise, normally nowadays we don't use it unless you have a gross leak in the breathing system or in the anesthesia machine. Without checking that, if you have started the anesthesia and you are holding the mask and the bag is not filling properly, then you may temporarily use the oxygen flush to fill up the bag and ventilate the patient. Okay. Otherwise, there is not much of use for oxygen flush, but it is one of the safety measures which has to be there to deliver oxygen. And you can see this is the modern anesthesia machine circuit selector, like what you have here between open and closed system. Here you have non-rebreathing and circuit system or rebreathing system. So when the pointer is in this situation, you will go to the circle absorber with the circuit system. When you turn this towards this pointer, you can attach your Jackson trees or other Beagle circuit. You can go to the open system or the non-free-breathing system. Okay. Then this coming to the components of the anesthesia machine group, as I said, and you have also answered, it is classified into high pressure, intermediate pressure, and low pressure. And these are all the components: hanger yoke, which we have seen; cylinder pressure gauge, we have seen; pressure reducing device, we have seen. And the intermediate, the central pipeline is classified as intermediate. Why? Why the cylinder is classified as high pressure, and why the pipeline inlet connection is classified under intermediate pressure? What is the pressure if you open a full cylinder of oxygen?
2000.
2000 psi. So naturally it will come under high pressure. But what is the pressure at which the pipeline connector supplies the gases to the machine?
45 yes.
45 to 55
45 to
psi.
55.
Okay, so that is why it is called the intermediate. When you come to low pressure, what will be the pressure in the low pressure system?
15.
14 to 15 psi. Okay, so 2000, 55, 15. That is the reason why it has been classified as high pressure, intermediate pressure, and low pressure. And this is another beautiful picture to show the components in different colors. So you can see the cylinders with high pressure, the pressure regulate the pipeline, I mean the pressure gauge, the pressure reducing valve, or the pressure reducer, regulator. All these things come under high pressure. And once they come to the next segment, it is the pipeline pressure, which is about 45 to 55 psi. All the oxygen failures or oxygen pressure fail supply devices, they all come under intermediate pressure. And then from the starting of the flow meters, where you normally operate to deliver the desired amount of gases to the patient, from there it becomes the low pressure system. Okay, so that is how the whole system is working. And the pressure system, how the pressure systems in anesthesia machine classified and what are the values? That is again what is the question I asked you. So this is the high pressure, which works at oxygen is 2000 roughly, whereas nitrous oxide is 750 psi. And the pipeline is 45 to 55 or 50 to 55, and less than that will become the flow control. Now, this is one important question that all of you should be able to understand and answer. What are the units of measurement of pressure and what is their correlation? Because in machine and vaporizers and other things, pressure in physics is measured in various units. Normally, when we talk about blood pressure, we say millimeters of mercury. But nowadays, it is being described in many textbooks in kilopascals. And if you see in anesthesia machines, many pressures will be described in centimeters of water, or it may be described in barometric or atmospheric pressure. So one should be able to understand what is the correlation between the various expressions or units that are used to measure the pressure. Okay. So how much is 1 kilopascal in millimeters of mercury? That is the commonest thing that we nowadays come across. In blood pressure, some books say kilopascals. Some books will continue to say millimeters of mercury. So if you say 1 kilopascal, how much that is equal in millimeters of mercury?
7.5 millimeters.
7.5 millimeters. Very good. So that is how you remember. So there are PSI, PSG, that is pressure gauge, pressures in unit at the gauge, and PSA. What is the difference between PSG and PSA? That is another important difference that you should know. Supposing you open the oxygen cylinder, a full cylinder, and it records 2000 psi pressure, pounds per square inch. This is called the pressure exhibited or displayed by the pressure gauge. But is that the correct pressure? I will put this question in some other way. Supposing you use an oxygen cylinder for giving anesthesia and the cylinder becomes empty. The pressure gauge now reads 0. Does that mean that the oxygen cylinder will not have any gas at all? It will be totally empty?
No, sir.
Huh.
It's related to atmosphere, it's 0.
So there will be another amount, small amount of oxygen still left in the cylinder, okay, which will be at atmospheric pressure because there is no gradient. Only fluids and gases always flow from an area of higher pressure to lower pressure. That is the basic physics. So what is shown in the gauge is the pressure exhibited by the compressed gas. To relate it to the atmosphere, you have to add the atmospheric pressure also, then it becomes the absolute pressure. Okay, that is how the whole gas is able to come out of the cylinder and come out of the machine because of this difference. You always add the reference point as 0 when there is an atmosphere or vacuum, but vacuum will not be there in the atmosphere. So the gauge pressure is always slightly lesser than the PSA, atmospheric absolute pressure, and that is the reason why the gas is able to come out and come out of the machine to outside. So the correlation between all these various units are 100 kilopascals will be equal to 1000 millibars or 760 millimeters of mercury, which is 1 atmosphere, or 1030 centimeters of water, or 14.7 pounds per square inch, and which is equal to 1 atmosphere. So this 760 only, if you say for 100 kilopascal it is 760, for 1 kilopascal it will be 7.6, which we roughly say it is at 7.5. Okay, so that is the correlation between these various measurements. Why pressure regulators are needed in anesthesia machines?
To prevent barotrauma.
Barotrauma, yes, because high pressure segment, they are delivering gases at a high pressure. Even their wall intermediate pressure is very high for our lungs to tolerate. So we have to reduce that. So pressure cylinders varies to make, and also the other reason is to maintain a constant flow by changing supply pressure. For example, if you start using a oxygen cylinder at 2000 psi, as the gas is being withdrawn from the cylinder, the pressure will keep dropping. So if there is a no pressure regulator, what will happen? The bobbin will be going on fluctuating. It will be dropping as the pressure drops, and you have to keep on rotating the flow meter knob to keep it at a constant level. So first point is it prevents barotrauma to deliver a safe pressure. Second is it maintains a constant flow without your need to adjust the flow meter every now and then. So it reduces the high variable pressure found in cylinder or to the lower or more constant pressure in anesthesia machine. And what is the physical principle involved in the working of the pressure regulator? How do they reduce that such high pressures into the tolerable 14 to 15 psi pressure? What is the mechanism? It is by a simple physical law. Okay, a large pressure acting over a small area is balanced by a small pressure acting on a larger area. Okay, so the pressure coming from the cylinder or the pipeline is a large pressure, but it comes out through the small nozzle or the small opening and enters through a small nipple into the hanger yoke and comes into the machine. Okay, so that is a very small area. Now you expand that area to receive that gas, automatically what will happen? The pressure will drop. So the principle is a high pressure acting on a small area is exposed to a larger area to reduce the pressure. Okay, so this is the mechanism. See, this is the inlet for the gas from the cylinder or a high pressure source, and this is a very small area in which it is acting, and there is a nozzle to push that, or a spring loaded valve is there, and once the gas is released to a large area like this, automatically the pressure drops. So by adjusting this diaphragm to increase or decrease this area, you can decide what pressure you want to deliver from this area. This is the outlet pressure. Okay, so a high pressure coming to a small area is released into this large white area, and the pressure adjustment, whether you want 20 psi or 30 psi, if you make this area smaller, the pressure will become higher. If you make this area larger by pushing the diaphragm away, it will further drop. So you can adjust this by adjusting the screw here. So this diaphragm moves up or down to increase this area, and as per the area present here, the pressure drop will happen and you will get a low pressure outlet. So this is a very simple mechanism by which you can understand how the pressure regulator works. And why pressure regulators are also called preset regulators. Earlier they were all called pressure regulators. Now the modern pressure regulators are all called preset regulators. What is the reason? The reason is now it is fixed at a particular pressure. You can decide at what pressure you want to deliver the gases to the flow meter. So you can set it at that. Earlier machines had as I told you, the screw can be adjusted manually by rotating it. So we can decide what pressure we want. And there were models like Adams regulator, where every time the anesthetist will rotate the cylinder, this screw to adjust the pressure. But that hassle has been removed now, and the manufacturers themselves, they decide and deliver the pressure at a particular level. So the name has been changed from pressure regulators to preset regulators, which deliver the gases at a particular safe level. And the cylinders fitted to the machine should always be kept closed when not in use. For example, if you are using both pipeline and there is a spare cylinder attached to the machine, should the spare cylinder be kept open or closed. And
Closed.
if it is to be kept closed, why it should be kept closed?
It should be kept close because the
Yes,
cylinder
it should be
pressures are
kept
high.
closed.
So we unknowingly will be using from the cylinders rather than from pipelines.
Yes, if the
In case
pipeline
of-
pressure drops, then what happens? If the cylinder is open, it will automatically draw the gases from this higher pressure. The cylinder pressure will naturally be higher. So machine will preferentially take the gas from the cylinder and the cylinder will become empty. So we should always aim to have a full cylinder for emergency use and not for regular use. So in machines fitted with central supply or pipeline supply, having a spare cylinder, we should always be able to use that cylinder when there is a unexpected fall or a complete cutoff of supply from the pipeline. But if you keep the cylinder open, what will happen? Even if there is a small drop in the pressure from the pipeline, the cylinder will be preferably used and cylinder will become empty. And in case you land up with an emergency, there will be no gas supply present. So always preferably keep the cylinders closed and use them only when there is a need to activate them in case there is a failed pipeline supply. And nowadays, of course, we have so much of safety mechanisms where whenever there is a drop in the pipeline pressure, we will get an alarm or a signal. So cylinder should be kept closed routinely. Otherwise, if the wall gas fails, the machine will automatically switch to the cylinder supply without the anesthetic being aware of the wall supply has failed until the cylinder is empty also. Okay. So now this is the old anesthesia machine which has been shown here, and I have masked the parts. Can you identify what are all the parts that are seen here? See, there is one marked here. This is another. These are the things which have been marked here. This is the third one. Have any of you seen these parts in your training so far? These are all the parts which in the old pneumatically operated Boyle's machine. Can you make a guess? There is a hole in this. And you can see this is the old type pressure regulator with the pressure gauge here. And
Relief
these are all
valve,
the,
sir.
this is the pressure relief valve. So whenever if there is a high pressure accumulating in this hole will let out the high pressure. Okay, so this is a pressure relief valve opening. These are the pressure regulators. Okay, and these are all the tubings. So safety relief valve. This is the vents. Even in the pressure regulator, there are small holes to release if there is a higher pressure accumulating. And these are all the metal tubings connecting to the flow meter as well as to the directly one line will go to the oxygen flush and another line will go to the flow meter. So this is how the tubings will be there. The parts of pressure regulator. Here, earlier it was called Adams pressure regulator. Of course, I don't think they will ask you all about this. The safety features in pressure regulator have safety relief valves. As I showed here, there is a relief valve here. There are small holes to relieve. Only when the higher pressure comes out, they will all be activated. And due to any reason, there is a buildup of pressure in pressure regulator, then the safety valve will blow up at a set pressure of 70 psi or above. Okay? Until then, it will hold on and let you work. The features of oxygen flush valve, which are present in our modern anesthesia machine also. What are the features? What is the pressure at which it delivers? What is the volume it will deliver? Already we have answered that. So it is 35
Intermediate
to
pressure system.
75 and it releases at 55 to 75 psi. Okay, whenever you use oxygen flush, why it can produce barotrauma? Because it is delivered at 55 psi compared to the 14 to 15 psi from the flow meter, which is very low. So the hazards are called barotrauma, dilution of inhaled anesthetic, accidental activation can constantly deliver a small volume and dilute your anesthetic agent. It can cause internal leak and sometimes the flush may get stuck in position and you will continuously get the delivery. So these are all the hazards of this oxygen. And why it is marked as O2 plus?
To minimize unintentional activation.
Under pressure. Okay, this is molecule name is oxygen and plus means it is under high pressure. So that is why it is been indicated as that. And some unique features are the flush valves are do not permit other gases to, you should not have that. Oxygen flush can be activated when whether the machine has electrical supply or not. Okay, even if you do not switch on the power supply, it will be activated, and the pressure delivered is at 55 to 60 psi, high pressure. So these are all the two types of oxygen flush valve present in two different workstations. What is the difference you see in these two? One on the left and one on the right.
There is a dip in the second one on the right, which makes it less handy for. We can't reach it very fast when we are placing the hands over the machine.
This is a guard to prevent accidental activation, whereas this is almost flushed on the surface. So even inadvertently, if your finger or your elbow touches this part, this will be activated. Whereas this is kept at a little inside or recessed area with a guard here. So accidental activation is prevented by this particular projection of a part of the machine. Whereas here it is easy to touch it because it is almost on the surface. So the symbol it has been caused is oxygen for molecule and plus indicates positive pressure. And there is the oxygen flush in this. Already I have shown you. You can see this here. And this is the close-up view. Now you can see this off written nicely here. So if you flip it down, it will get activated. So this is how the oxygen flush in the older machines are there. What modifications are made to oxygen flush in the workstation? Already we have seen that being done. This is the same question. What is the mechanism of working of that oxygen flush? So when you push this button, what does happen? So this is the valve mechanism. So when you push this button, there is a lever going in and then it is releasing the valve and the oxygen will start flowing. Then it's a spring-loaded valve. What you see here is a spring-loaded rod which will go and open the valve here for the oxygen to come directly from the pressure regulator and it will go out to the breathing system. So this is the inside drawing of that. Now again, this is another picture of the bottom portion of the old anesthesia machine. So there are a few parts which already we have seen, but more parts are being named here. Can you identify those parts? All the arrows that are there. This arrow, very easy. What is this?
Pressure
Gauge. Okay. This arrow already we have seen. What is this? It is attached to the pressure gauge. Huh?
Pressure regulator.
Pressure regulator. Very good. Okay. So this is again a pressure regulator. What is this? What are all these tubings? This tubing coming here. This is the oxygen flush. This is the oxygen flush. This is the tubing coming from the pressure regulator to the oxygen flush. And these are all the various connections that are there. Okay. So you can see this is a pressure gauge. This is the pressure regulator which we have already seen. This is the ventilator outlet. This is the oxygen flush. This is the fresh gas outlet. This is the nitrous oxide pressure gauge. This is the nitrous oxide pressure regulator. And these tubings here, they are the ones which go for low pressure alarm system. So we will see that anesthesia machines are designed in such a way that hypoxia should not happen heterogeneically to the patient. So the basic principle involved in that is, one is, if there is a drop in oxygen pressure, which is the life-saving gas, immediately the machine should alert the anesthesiologist. So the first half of the safety mechanism is to alert the physician about the reduction in the oxygen supply pressure within the machine. Okay, that is the first half. So this is where your low pressure alarms all work in the intermediate system. And once it comes to the flow meter, there is a hypoxic guard to prevent lower volume of oxygen being delivered. So the oxygen safety mechanism can be divided into two parts. One is prevention of dropping in the oxygen supply pressure within the machine. Second is supplying a hypoxic mixture with along with the other gases. These are the two things that have to be taken care of. So all the low pressure alarms are all situated in this area. Okay. And once it goes to the flow meter, there you will find that however much the days of using nitrous oxide, now most of us are switching over from nitrous oxide to medical air. So there is no fear of giving hypoxia at any point of time. But when nitrous oxide is being used, you are likely to deliver a hypoxic mixture. So all the machines have provision to supply minimum of 25% of the total mixture should be oxygen. Okay, so for that we have what is called the hypoxic guard or the link 25 mechanism, which we will be seeing later. Okay, so the mechanism or alarms that are present in this intermediate area, they tell you about the drop in oxygen supply pressure after they are being released from the pressure regulator until they reach the flow meter. Okay, in that level, if there is a drop, immediately you get an alarm that is called the oxygen supply or pressure fail alarm. Whereas what you get are the alarms that are situated in the flow meter level is the hypoxic guard or hypoxic alarm. Is it clear? Now coming to the flow meter part of it, which becomes the entry point of low pressure segment, you have what is this flow meter? What is this? What is the difference between these two? You are able to see the pictures?
Dobbs tube.
Just see the picture and tell me how many, is it the same gas which is going through both the tubes
Yes,
here?
Yes,
It is in millimeters
same
and
gas
liters per
through.
minute, sir.
Ah.
One is in millimeters and other tubing is liters per minute, sir.
So this is a twin flow meter, okay, connected to each other. What you have in your normal modern workstation, you have two tubes for each gas, isn't it? Oxygen, you have two tubes. Nitrous oxide, you have two tubes, and air, you have two tubes. Why you have two tubes like this?
To facilitate smaller
Low flow
Ah.
anesthesia, sir.
Low flow anesthesia. Nowadays, the concept is to use as minimal amount of gas as possible to avoid number one wastage and two to remove the unnecessary pollution that will happen if these excess gases are vented out of the machine. Okay, so that is the main reason we are now using the concept of low flow anesthesia, where there is a minimal flow, metabolic flow, basic flow, all those things are there. So sometimes we reduce the flow as to even 500 milliliters of oxygen to 500 milliliters of air or 500 milliliters of nitrous oxide, whatever you are using. So for providing an accurate delivery of a low flow, we have the first tube which is graduated or calculated from 100. Nowadays even there is 50 in some of the newer machines up to 1000 ml. And if you want a higher flow at the end of the surgery, when you want to reverse the patient, you have to give a higher flow. Then you have the second tube which will deliver from 1 liter to 10 liters. Okay? So this is the concept of two twin flow meter tube, one for low flow, another for higher flow, and that is called the fine flow and coarse flow also. But in situations where these two tubes are not available, then the same tube will have different type of expansion. See, actually the inner diameter of the tube will be going on expanding up to 1 liter. It will expand at 0.4, 0.6. Then it will expand suddenly much broader, and it will deliver both the low flow as well as high flow within the same tube. So this is how this is a constant pressure variable orifice flow meter with a two tube design, and this is called the dual taper design. Okay? Double taper or a dual taper machine to deliver both low flow and high flow in the single tube. So what is the flow meter tube called and what is the material it is used in making it? Somebody mentioned the name here. It is already given here. Are you able to read that?
Tops tube.
Torque tube. Yes, is the person who designed that. It's called the torque tube. And what is the material it is made up of? Borosilicate. So it is nothing but a glass, but a more sturdy type of glass called the borosilicate glass. Okay. And what is the purpose of single and double tube? We have already seen when there are separate flow meter tubes for low flow and high flow, the same gases can be then or it can be sent as a single tube. So if there is a single tube, then it is called double taper. Now, how does this bobbin, when you open this control valve, how does the bobbin that normally you see in your flow meter rotate? What is the mechanism? Where do the gases flow from? In this picture, if you see, the gas is flowing here. Once you open the valve, it flows out to the top and then goes out like this. So how does the bobbin rotate as you see in your day-to-day machine? Have you all not seen the bobbin at a closer?
Clockwise.
Huh?
Clockwise rotation.
Clockwise direction. How is it rotating? What makes it rotate? Because of the slots present in that. If you see here, you can see these are all the cuts that is present in the top portion. Okay? It is like a conical. This is the normal bobbin, or this may be the bobbin that you'll be seeing in your machines. We don't see the ball type or this eye type in many of our machines. So it may be either of these two. And it has got a slanting groove on the upper one. So when the gases flow through this groove from down, it rotates the bobbin. Okay. So the bobbin names are, this is called the ball type. This is the non-rotating bobbin. This is the skirted. This groove is called the skirted and non-skirted. So all these four types this is the common type that we will see, and there will be a dot for you to identify that it is rotating. What are the conditions it will prevent rotating? In which condition, even though the gas is flowing, the bobbin may not rotate? This is one of the common questions they ask you in the exam. Post DA candidate Gayatri, are you there? Mr. Gayatri, are you there? Are you all able to hear me?
Yes, sir. If there is any breakage in the glass of the flow meter.
Breakage. All the gases will leak out. There are two reasons why the bobbin may not rotate. One is called static electricity. Usually the inside of these flow meter tubes are all coated with a substance to prevent static electricity. But if their coating has worn out due to wear and tear, then the bobbin may get stuck because of the static electricity attracting the bobbin towards the wall of the flow meter. Or dust may accumulate and that may block the rotation of the bobbin. So these are the two reasons that answer you have to give. One is the static electricity, second is the dust in the flow meter inside tube. So these are all the parts of a flow meter starting from the outside which you normally use every day, and you have to know how these gases are flowing. So I have marked the parts. Now can you just try to name them? What is this? This is the control knob that you are using every day to open and close the gases. Okay, so once you operate that, what happens? These are all there is what is called the needle valve. This needle valve will be pushed back and gases will start flowing from here towards the flow meter tube. And what do you think these two are? One here and one there. None of you have read the books at all. So flow control knob is here and there is a valve stop. You cannot rotate this and make it flush with that. So it will be closed only up to a particular level to prevent damage to this needle valve. So this is what is called the needle valve, and when you operate it anti-clockwise it opens, when you operate clockwise it closes. And once the needle is withdrawn here, oxygen from the inlet will come into the valve here and then flow through this. And there are two stops here. One is called the lower stop, float stop, another one is the upper float stop to prevent the bobbin dropping down below this or going up above that. Okay, and this is the bobbin or the float, and this is the tapered tube, inside tube, which is the expanding slowly from below to upward. Okay, so that is the construction of the flow meter tube. So remember, flow control knob, needle valve, inlet for oxygen, valve stop to prevent complete flushing of the knob to this portion of the machine, and float stops on both up and top and bottom, and this is the float or the bobbin, and you can see gases flow around the bobbin, and when there are skirts in that it starts rotating, and the tube gradually becomes broader from bottom to top. It is not the cylindrical uniform inside, it is a broadening from, it is more or like a cone. It is narrow at the bottom, and as it goes to the top it becomes expanded. Now this is a very common thing that all of you are aware. What is being shown here? Can you identify all the things that are shown in this?
Oxygen, nitrous, and air flow meter.
There are twin flow meter tubes for three gases. Nitrous oxide is there, air is there, oxygen is there, with their float or bobbins at the bottom position. That means they are not being opened. Very good. Then what else you see? So these are the control knobs for all the three gases with a color coding, with the flutes. That is the grooves that are present. These are called the flutes, F-L-U-T-E-S. So that is very large in oxygen, very fine in nitrous oxide, and you see coarse in air. And there is a color coding green, yellow, and blue. What are these two?
Auxiliary flow meters.
Auxiliary flow meters. Very good, for air as well as oxygen. And what is this? This long rod-like thing in front of the knob.
To prevent accidental.
This is a guard. You must always say this is a metal guard to prevent accidental activation of these knobs. Okay, so all these things you should be able to say. It's a twin tube for nitrous, air, and oxygen. Control knobs with color coding, name written, and the direction to show from opening to closure, and the guard, metal guard to prevent accidental activation, and auxiliary flow meter tubes for both air and oxygen. Okay? Uh, so protective guard, auxiliary flow and all that. What are the safety features of that? Of course, flow meter knobs are color coded, chemical formula is written, oxygen control knob is bigger in diameter and more fluted compared to the other two knobs. So these are all the questions they ask you. Safety features in these knobs. And flow control knobs are recessed or protected by shield like this. Okay, it can have side protection also. It need not be always a metal frame like this. It can be side protection. And fluorescent back panel is there in some of the machines. This back panel sheet that behind the flow meter tube that may have a fluorescent panel to give illumination in the night. In case of dark, some surgeries in the ophthalmology department, retinal surgeries are done in full darkness. So in such situations, or some arthroscopies also, the surgeons want the theater to be less illuminated. In such situations, you have to be able to see the flow meter. So it may have a light here or it may have a fluorescent back, and oxygen to nitrous oxide ratio controller or proportional system to prevent hypoxic mixture, and anti-static coating to prevent the bobbin or the float getting stuck. All these safety features in the flow meter. Why is it preferable to place the oxygen flow meter in the first position instead of the third position as you see in some machines? There was a lot of confusion. Earlier, when they manufactured the machine, they first kept oxygen, then nitrous oxide, then the other gases. Then in the later models, they switched to oxygen to the last position and shifted nitrous oxide to the first position and air or other gases in between. Now again, they are coming back to the oxygen in the left extreme or the first position, then air, then nitrous oxide like this. The reason why is, if you see this, the oxygen, if you keep it in the flow, that flow meter goes beyond all the other things as a separate line. Okay, so even if there is a crack in other things, flow meter tubes, the oxygen delivered will be fully supplied all the time. On the contrary, if you have a oxygen in the second position and there is a crack and the other gases come in the set volume, then it will dilute the oxygen and produce a hypoxic mixture. But if there is a crack in this tube here, nothing can be done. That will also produce a hypoxic mixture. But assuming that the oxygen flow meter is intact and the other flow meters have a crack, then having oxygen here will ensure that you will have a normal oxygen supply without dilution from the broken cylinders. Now, what is this picture showing you? What is the name for this?
D-Link 25. D-Link
It's
25.
called Link 25. Very good. Why you call it as Link 25?
What are the mixture of gases being delivered? In that 25% will be oxygen.
Oxygen. You are assured of 25% of oxygen. Excellent. Very good. So that is how you can see there is a sprocket with a wheel. Okay. So the wheel for the oxygen is bigger, which has a 28 teeth, and this is a 14 teeth, just like your cycle chain. And when you rotate one time the nitrous oxide, the oxygen will rotate twice because it has got 28 teeth sprocket. So you will be definitely assured of 25% of oxygen supply. Okay, so this is called the Link 25 system. So this is present in modern anesthesia machines, and this is the reason for the hypoxic guard device. This prevents inadvertent delivery of hypoxic inspired gas mixture, The ratio of oxygen to nitrous oxide will never decrease below 25% or 0.25. Okay, so you are always assured of 25% or 25% oxygen in the mixture at whatever given time. What is shown in this? What are all the things that you are seeing? Are you able to
Main
read this?
Power
Maybe-
switch,
Power supply.
auxiliary.
What is this? You are seeing your workstation every day in your OT.
Yes, sir.
Now, what is this? Whenever
Power
you
switch.
find the
Power
symbols,
button.
what does it mean? Huh? It's a power on off switch. Okay. So this I means on, this means off, and this is a light indicator. Okay, show a green light when you put it on. And you can you read this? The alternate oxygen control. What is the importance of that? And it is written here on off. This is another safety
In case
feature.
of power
Ah,
cut. For half an hour,
Ah.
it will give uninterrupted supply of oxygen as well.
yeah. Even if there is a failure of oxygen from the pipeline or due to electrical supply failure, still you can get oxygen through this flow meter by operating this. And you have a on off switch button for that. So you press it, it will become on, you can get oxygen delivery. So all the aim is to prevent hypoxia happening because of wrong delivery. Okay. So this is again the pressure gauge for that. What is this? Have any of you seen this in your stations? Those who have worked in SRMC, they may have seen.
No, sir.
Huh? This is a vaporizer. Can you tell me the name of the vaporizer?
Anaconda wave.
Anaconda is used in ICU. It also starts with A. It's called the Aladdin vaporizer. Okay, so Aladdin vaporizer. So what you are seeing is the master switch, which activates the working station. Then you have the gas flow for control knobs and indicate flow freely a point when there is a downward equal to upward. Why the bobbin floats is another question that they may ask you. It is because of the downward flow acting on the gravity acting on the bobbin opposed by the upward flow of the gases. That is what is making the bobbin flow. Okay, so more the gas flow, it goes more up, and the diameter increases. The periannular space is increasing, and that is how the more gases are able to flow through this. And the factors governing the flow of gases in the flow meter tube, there are three factors. One is the pressure drop across the constriction. Between the gas flows around the indicator, it encounters frictional resistance between the indicator and the tube wall, and there is loss of energy, which is reflected by a pressure drop. This pressure drop is given by the formula weight of the float by the cross-sectional area. Okay? Then the size of the annular opening, that is the space around the float, that is the annular opening, which increases as the flow increases, and the physical characteristic. This is a very, very important thing. Every gas has got two properties. One is called the viscosity, another is called the density. All of you would have learned about it as a high school student itself in physics. What is the difference between density and viscosity?
Laminar flow depends upon the viscosity of the gas.
No, I'm
Whereas
not asking
the-
about the relationship between the flow and this thing. What is the simple meaning of the
Density
word
is-
density and viscosity?
Density is mass per volume, sir.
Density is the mass per volume. Very good.
Viscosity is the resistance to flow.
Resistance to flow. Excellent. So whenever viscosity is high, will it have low flow or high flow?
Low flow, sir.
Low flow, it will be sticky, just like your difference between water and honey. If you take a spoon of water and pour it, water will drop easily, whereas honey will take a long time to come out of the spoon, isn't it? Simple example which is given in school. So viscosity indicates the resistance against which the flow has to occur, whereas density indicates the mass per volume, rightly said. So at low flow, which one works? Which one is important for the flow to happen? If you use a low flow
Yes.
anesthesia, you are using only 250 or 300 ml of oxygen and 300 ml of air. Which property of the gas will come into play? Anish, you started answering that question. Your answer was right.
Density of the
Low
gas.
flow will be laminar. That is, all the
Laminar
air passage will be parallel to each other, and it will have faster flow at the periphery and the smaller flow towards the center. That is called the laminar flow. What is turbulent flow? Gas molecules bombarding with each other. They make a somersault and try to hit with each other. That is turbulence or agitation. So in turbulent flow, which one will be important?
Viscosity.
Density.
Density.
Laminar flow, it is viscosity. So remember LV, left ventricle. Laminar, viscosity, turbulence, density. Okay, this is another common question they ask you in the examination. So low flow, small annular space, therefore there is a laminar flow. So the function of gas becomes dependent on the viscosity. Whereas high flow, larger annular space, the flow is turbulent and therefore the function is dependent on density. So remember the mnemonic LV, left ventricle, always laminar, viscosity, turbulent, density. Okay. What is shown here and what are the advantages and disadvantages of this? Of course, this sort of this may be seen in some hospitals where they have this sort of component in the anesthesia machine, but not a very commonly used like other thin flow meters and other things what we have seen. So just at least by reading, looking at the picture, can you just identify what are all the things you are seeing?
Digital flow.
This is the digital display of what are all the things that are being displayed here?
Oxygen, nitrous,
Oxygen in
air,
2 liters per minute.
2 liters per minute. Air at 1 liter per minute. Nitrous at 1 liter per minute.
1 liters per minute. And how many flow meter tubes are there?
Only one flow meter tube.
Only one tube is there. Okay, so this is an electronic flow meter. Okay, showing digital display. Information can be sent to data management system from this, whereas it requires electric power all the time to operate. Okay, this is a disadvantage of this particular electronic flow meter, which is seen in some machines but not in all commonly used machines. What is shown here and what are its features? A different model of already what you have seen. And you are seeing, are you seeing the yellow arrows here?
Yes, sir. Auxiliary oxygen.
There is an auxiliary flow meter for both
Oxygen as well as
and the air. And these are the, what are the pointers showing it? One yellow and one green. Outlets. Okay, so you
yellow
can,
is outlet.
it's an auxiliary flow meter found on workstation. It is a self-contained flow meter with its own flow control valve, flow indicator and outlet. It's a short tube with maximum flow of 10 liters per minute. Usually on the left side of the machine, we can use to supply oxygen to patient without turning on the machine. It doesn't require the electrical supply or electrical power. Older machine works on pipeline supply, whereas in the newer machine, it works on both pipeline as well as in the pressure, cylinder pressure. It is the cylinder there. Now, what is being done here? There are two red arrows showing here. and there is a flow meter which is connected to the common gas outlet with an adapter. Anybody who can identify why they are doing this? And you can see all the arrows pointing here. This is to find out the internal leak. Even if all the flow meters are all in off position, sometimes if there is an internal pipeline leak in the workstations which we are using nowadays, you keep all the flow meters in off position, and then you connect the common gas outlet with an adapter to a plastic tube and a flow meter, and keep this oxygen flow meter which you use in the ward for supply in the open position. So what will happen if there is a leak? Leak will have to come out only through the common gas outlet, and that will go through this tube and it will raise the bobbin in the oxygen flow meter that you use in the ward or in the ICU. Okay, so that is the method of finding out the internal leak. So flow meter connected to the common gas outlet to quantify the internal leak, and what is being shown here? This is called the transitional hybrid flow meter, where instead of depending only on the electronic system, you can use both the manual as well as the electrical thing. So this is the manual, transgrid hybrid flow meter. Sometimes if they show this sort of pictures or if they have machines like that, you should be able to identify, and that is the reason why I put this. So there is a needle valve, so flow can be generated even without electric power, and flows are captured and displayed electronically. So the electronic flow meter allows automated anesthesia record keeping chart to go on. So these are all more high-end sophisticated machines which may be used in some institutions. What are the oxygen failure safety features in the anesthesia machine? Already I have told you there are two things. One is the pressure drop failure. The other is the hypoxic mixture delivery. So these are the two things which have to be prevented. So the pressure sensor shut-off valve will automatically cut off the nitrous supply if there is a drop in the pressure. And oxygen failure protection device is also there, which also whenever oxygen pressure decreases, that also will cut off the nitrous oxide supply. This mechanism in dataxometer machine is called the fail-safe pressure sensor cut-off system. Okay, and here when the PSI, the oxygen pressure drops to less than 20 PSI, the flow of all other gases, whether it is air or nitrous oxide, everything will shut off, and then immediately the second stage oxygen pressure regulator is the one which will allow this to happen. And this is a picture to show how nitrous oxide will also stop flowing when the oxygen pressure is dropping. So when there is a 50 psi oxygen pressure, nitrous oxide also flows at 50 psi. When the oxygen drops to 25, you can see the nitrous oxide also gets reduced to 25. And when there is no oxygen supply, nitrous oxide is also totally stopped. Okay? So that is how the whole thing works on. And the audible alarms to indicate that there is a hypoxemia, there are two methods. One is called the Bowman's whistle, where pneumatic alarm uses a pressurized canister that is filled with oxygen when the anesthesia machine is turned on. And when the pressure falls below a certain level, again this alarm will, so this will work every time. When you switch on the machine, initially it will give an alarm or a sound. Then when there is a drop, it will continuously blow. And that has to be happening within 50 seconds when the PSI drops to less than 30 PSI. Okay? So these are the, and there is another thing called Ritchie's whistle also. This is again another picture of link 25. Other hypoxia prevention methods are minimum mandatory oxygen flow. So some machines require a minimum of 50 to 250 ml of oxygen flow to before other gases start flowing. So you are always ensured of minimum of 250 ml of oxygen, and some machines activate an alarm if oxygen flow goes beyond a certain minimum. And there is another minimum oxygen ratio where you have more than 21% available, and this mechanical linkage is the link 25 system. So these are all the measures to prevent the hypoxemia. And this is oxygen ratio monitor, again works on the same principle between the pressure between the two systems. This is again the older picture as I showed you. This is the alternate oxygen with a knob to store all the so it gets activated when there is a drop in pipeline or backup cylinder pressure, and the idea is to deliver oxygen at all parts. So identify the parts of the machine displayed here. This is a modern machine which all of you are aware of. Now can you identify what are all the parts that are shown in this?
Adjustable pressure valves.
Adjustable pressure valve, this black one, okay. Then
CO2
what is this?
absorber.
Carbon dioxide.
Carbon dioxide absorber, very good. What is this? Telephone wire மாதிரி ஒன்று இருக்கு. This white thing.
ETCO2 cable.
ETCO2 cable. ETCO2 இங்கே கனெக்ட் பண்ணணும், லீக்கிங் சர்க்யூட்ல கனெக்ட் பண்ணணும்.
Oxygen sensor.
Tomorrow when you go to the theater, you see whether you have this in your machines or not. This is the oxygen sensor which displays what is the percentage of oxygen you are delivering to the patient. Okay, this is the most important part of your anesthesia machine. So this is the oxygen sensor with the cable. This is the APL valve. This is the airway pressure guard. And these two small plastic domes, what are they?
Inspiratory, expiratory valve.
Unidirectional valve cover. Okay, they cover them, show you the unidirectional valve flipping in and out. You can see one working during inspiration and another working during expiration, and this is the outlet. Okay, so these are all the parts that you see. What is this hook for? Can you see a hook here? Not all machines will have, but some machines, this is a Pendon machine which may have that. So these are all the oxygen analyzer, white part with a coiled white wire, APL valve, unidirectional valve covers, airway pressure gauge, and CO2 absorber. And this is the handle to remove the absorber and replace the replaced cylinder. Now this is another machine, a view of the same machine. Already shown you of this. Can you identify these parts?
O2 flush. Common
Oxygen
gas
flush,
outlet.
very good.
Common
What
gas
is this?
outlet.
Common gas outlet is this.
Open close system switch.
It's a switch to select between rebreathing and non-rebreathing, a circle system and open system. Okay, so this is the technique. So circuit selector switch for open and closed breathing, oxygen flush valve switch. This is again a picture which you have already seen, but can you identify all the parts in this? This gas is being used or it is in off position?
Gas is being used.
Used.
O2 and air.
So you can see the float is not on the bottom. This is here, it is zero, whereas it is on use now. Is it being used in high flow or low flow?
High flow.
High flow, because it is in the second tube. Okay, first tube is empty. So the float is now on the second tube focus. So probably the first tube float would have been gone up because it has gone up to the maximum level. So it is the high flow that is being seen in the tube. And what are all these things?
Gas pressures.
Pressure gauge for both pipeline as well as the cylinders. Okay, panel. This is called the pressure gauge panel. What is this?
Master switch.
Master switch. Very good. And again, this is the metal guard which you have seen already in the other picture. Okay. So twin flow meter tube with oxygen and air on flow. So the first and three are opening. Okay. So both the oxygen is on and air is on, and the flow control knobs, protection guard, pressure gauge for gases, master switch for power supply. All these things are being seen here. What is shown here, which we have already seen there.
Pressure
Pressure
release
release. Maybe yes, it is pressure release valve. Prevents high pressure being transmitted to the machine. Whenever preset pressure is exceeded, valve opens to atmosphere and gas is vented outside. And whenever the usually opens when the pressure exceeds 35 kilopascals. And it's also known as the pop-off valve. Again, the features of common gas outlet. Receives all the gases and vapors from the machine and delivers the mixture to the breathing system. Some outlets have 15 mm female slip-in joint fitting or coaxial 22 mm male connector. The machine standards, it is difficult to accidentally disengage the delivery hose from the outlet, and the pressure delivered is 5 to 8 psi above atmosphere. So it is not just a 5 psi, psi A. And all of you would be aware of this sort of dome, the unidirectional valve. Okay? So check valve. What is the purpose of flow meter? Already we have seen that. And twin flow meter for low flow, having a first tube 50 ml to 1 liter and the second 1 liter to 15 liters depending upon that. And this is again a single flow tube display with a flow meter. And this is another picture of an electronic flow meter with a touch control screen. So you can adjust all the flow with your fingertip just as you do the touch control monitor. This is the role of back bar. What I told you is that this is the entire back bar in the old machine starting from the flow meter. This is called the flow meter manifold, and all the gases that you use will flow here and flow through this tube across that through various. So in the older machine, this is called the back bar, where all these attachments are there. In this picture, you can see there are 3 flow meter tubes which have their control knob. Can you identify what is this color knob for? This picture more of historical importance. Some hospitals may still have machines like this, which they prefer to keep and see whether the students are able to identify them.
Ether, sir.
This is ether is a liquid. Ether is present in this bottle.
Halothane.
It is not a gas. Flow
Enternox.
meters are mainly for gases, not for liquid anesthetic agents. Liquid anesthetic agents are dispensed by vaporizers. Okay, whereas this is for cyclopropane. And there is a 4th tube which is dummied with a metal tube. You know what it could have been used for? They were using it for carbon dioxide. In the earlier days, whenever they were doing general anesthesia, they used to give carbon dioxide at the end of the surgery. What is the logic behind that? What is CO2 supposed to do to the respiration?
Stimulates the respiration.
Stimulate the respiratory center and wash out increase the tidal volume and ventilation and wash out the anesthetic gases. That was the idea. But later they found that carbon dioxide itself can accumulate in the body and produce carbon dioxide narcosis. So they removed it and dummied this. So that is a small historical story behind that. So they are used for oxygen, nitrous oxide, and this orange color is cyclopropane. One flow meter which is made dummy has been used for CO2, which is not there. What is shown here and what is unique about it?
Desflurane vaporizer.
You have a desflurane vaporizer. What is this?
Sevoflurane
Name
vaporizer.
is also written here.
Sevoflurane.
Sevoflurane. So there are two vaporizers which are fitted here. And what is unique about it? It's a Draeger machine. You can see, read the name also here. So shown the vaporizers for sevoflurane and desflurane. The answer is correct. They are interlocked so that they can be used one at a time only. You cannot use both. Okay, so interlocking system is there. What is the purpose of interlocking? How was it done in older models? Purpose of interlocking is to use one agent at one time. Okay? Prevents using two agents simultaneously, which may result in the agent with a higher boiling point condensing and mixing with the one having a lower boiling point. Okay. So how should they be arranged? So when you arrange the vaporizers, you should arrange the one with a higher boiling point at a older machine vaporizers for the agent with a higher boiling point is placed downstream to prevent the condensation of the one with a lower boiling point. Okay. The downstream means at the extreme position. What is the checklist to be followed before use of a machine? What are all the things you have to suppose? Nowadays, probably the OT assistant or the anesthesia technician is doing all the job for you. So as a anesthesiologist, most of the time, you just go and start the case. But the exam, they may ask you what are all the steps that you have to follow or check before you start anesthesia with the machine, which is very important as a practical point also, because sometimes a newer technician may fail to do the correct method of checking. So you must also be aware of how to check the machine.
To check power supply
Very good.
present or not, and
Hmm.
we should have a backup oxygen cylinder
Oxygen
mounted.
cylinder. Excellent. Very good. Fantastic. Then
And we should check the pipeline pressures.
Okay, very good. So first identify the source of gas, whether it is from the pipeline or whether you are going to use the cylinder in the machine. Okay. Then you see, open and see whether the pressure gauge is showing adequate pressure inside the cylinder. Okay. Right. Then will you open the flow meter and see whether all the gases are flowing?
Yes, sir.
Yes, you have to see whether they are flowing or not. Will you
And to
check for hypoxic guard?
Yes, sir.
How to check for hypoxic guard, which I told in the last class?
While closing, while the nitrous should not flow alone. It should close along with oxygen.
Anish, I think I told about this very clearly in the last class. How to check the hypoxic guard.
Yes, sir. You have to use that self-inflating bag.
Self-inflating bag. Hypoxic guard க்கு அது flow meterல எப்படி வருதுன்னு பார்க்கறது பண்றது hypoxic guard test.
Yes, sir.
I think you have not listened properly.
I listen, sir.
Yeah, right. So I will tell you again. First, open the oxygen flow meter, keeping the other flow control knobs in off position. Okay, say raise it to 5 liters or 2 liters or 3 liters. Open the oxygen to allow oxygen to flow. Then open nitrous oxide to the same volume. Okay. Say first you have raised oxygen to 2 liters, you raise nitrous oxide also to 2 liters. Then you close the oxygen knob. Then what will happen? Oxygen will come to 0. Immediately what should happen?
Nitrous also fall down, sir.
Nitrous oxide also should drop and come to 0. Okay, that is the safety mechanism. So you cannot supply nitrous oxide without oxygen at any time. This is how you test for hypoxic guard. Open the oxygen. The other method is you first open the nitrous oxide. Automatically oxygen also should flow to the equal volume. Then only the hypoxic guard is working. So these two methods you can use. But I prefer to use the first method because if oxygen is flowing, that means the oxygen pressure is also normal and oxygen will start flowing when you open that. And you open the nitrous oxide, both of them are flowing. Then you close oxygen. That means if there is a drop in oxygen pressure and oxygen starts dropping, automatically nitrous oxide also should come down and drop. No gas should flow. That is the method of testing. Otherwise, open nitrous oxide first, immediately oxygen also should flow to the equal volume. That is also another method of testing for hypoxic guard. Okay. So they check availability of working suction, ambu bag and defibrillator indicator, first thing. Then the second thing is identify the source of gas supply to the anesthesia machine, whether it is coming from central pipeline or the cylinder attached to the machine. Perform the tuck test at wall outlet to ensure secure connection. And in case of central pipeline supply, make sure the full oxygen or half full oxygen cylinder is always available and attached to the machine with its key to open the cylinder. That is very, very important. Sometimes, people make sure just have a cursory look, there is a cylinder attached. But when it comes to emergency, the key to open that cylinder may not be there. So it is preferable to have the key to open the cylinder valve all the time on the spare cylinder and check the flow of oxygen from auxiliary flow meter. In case of emergency, you should be able to deliver that. Turn on of the mains power supply. Check for oxygen, nitrous oxide and oxygen flow through the flow meter. Check for hypoxic guard by opening oxygen and nitrous oxide. Close oxygen, nitrous oxide flow should stop and resume only when oxygen is opened again. So this is the common method of testing. Inspect the vaporizers for agent level, whether the filling port is properly closed, whether the dial is in 0 position, and check by opening and closing the dial setting whether it is freely working or not. So these are all the steps that you have to follow before using the anesthesia machine in a day-to-day practice. How is the integrity of breathing system checked? That is, there is ensuring that there is no leak or anything. How do you check for the integrity of the breathing system? See,
By
every day you are
attaching the
doing huh?
inflating self-inflate, by attaching the reservoir back to the one end and uh, and to see whether the bag is filling or not. That
Tank is filling or not. So you require 2 bags to check. One
yes,
is
sir.
the
2
reservoir
bags.
bag attached to the limb
The
where
white
you
piece.
ventilate. The other is you want to attach it to the patient end and then check. Is it always required? Do you have always 2 bags in your OT for every machine?
Yes, sir. I have 2 bags.
So that is how you have been taught. Supposing you don't have a second bag, what will you do? Right. See, first
Use my
what you
hands
do
to
is,
occlusion.
huh?
Occlude with the hand.
Close the pop-off valve. Okay, the APL valve that you found in that black thing, the previous picture, you close it completely. Occlude the breathing tube by placing your hand or the thumb to the connection port. Then pressurize the circuit with 30 centimeters of water by using 3 liters of oxygen flow to fill the bag. Okay. Then turn off
Okay.
the oxygen flow and watch the pressure gauge for pressure loss. Because you have a pressure gauge there to tell you whether there is any leak or not. Then turn on the vaporizer with no oxygen flow and watch whether there is again a pressure drop. So at any point, if the pressure loss is detected, increase oxygen flow slowly until the pressure holds steady. Okay. So the amount of oxygen that is required to fill the or keep the pressure gauge at 30 centimeter, that is the rate of leak. So you can check the integrity of the circuit as well as the vaporizer by doing this test. This is a very, very important test, all of you know. And it is not necessary always to have a second bag. All you have to do is occlude the patient end where you connect the mask or your endotracheal tube with your finger or your hand, and then first open the
Hi.
oxygen flow meter to 3 liters until the reservoir bag becomes full and the pressure gauge shows a pressure of 30 centimeters of water. Then close the oxygen and see whether the pressure maintains at 30. And you can visually see the bag also will start becoming some if there is a leak. So that is how you check for that. So confirm leakage does not exceed 300 ml per minute. If the leak is more than 300, the leak needs to be addressed. Then open pop-off valve and confirm release of pressure. That is, once you open the valve, the pressure gauge should come to 0 from 30 centimeters. Then checking for scavenging, confirm connected to pop-off valve, turn on extractor and confirm rate of extraction. And check ventilator function if there is push. So these are how the breathing systems are checked. Okay. So that concludes the discussion of the anesthesia machine. Can anyone tell what we have not discussed so far in these 2 classes? Kalpana, Harita, Aravind has come. What we have not discussed, which is a part of anesthesia machine.
Last class I was not there, sir. So I don't know.
Ah.
We discussed.
And that's why I gave a recall of what we talked
Yes.
in the last class.
Uh,
For your benefit only,
yes, sir.
I first narrated what all things we discussed in the last class as a rapid recollection.
Yes, sir. I saw that, sir.
So what is the important part of an anesthesia machine we have not talked about? Can you give anesthesia with only oxygen, air and nitrous oxide?
No, sir. We have to use anesthetic gas.
Have we talked anything about the vaporizers?
You just mentioned about vaporizer and interlocking systems.
We just mentioned about the interlocking. We just mentioned only a few things about the attachment of where they are. We have not talked anything about that. But vaporizers form an important integral part of anesthesia machine because we use them regularly to maintain the anesthetic state of the patient. The depth of anesthesia is dependent on the vaporizers which we use. So we have to learn about the vaporizers also, which also forms part of learning of the anesthesia machine. So we will now just go to see what is your knowledge about the vaporizers. Are you able to see? Is the
Yes, sir.
screen visible?
Yes, sir.
Okay. This already I've shown you. What is being done here? It's the open drop method of giving anesthesia
Yes.
using Schimmelbusch mask and Bellamy Gardner bottle. Okay. So I will go through this rapidly. They're all the open drop method where initially we used to use an agent called ethyl chloride, which was used as a spray. Because it has a boiling point of only 12.2, the pressure inside will be twice the atmospheric pressure at room temperature. So it comes as a spray, and this is the control lever to allow the vapor to come out. And it is used to as a pleasant smell. So before ether, we used to spray this to patient to go under with a pleasant inhalation, and then use it. It can be used as a topical spray also to produce refrigeration. Because once you spray that, the skin will become cool. And we used to make incision and drainage procedures for large abscesses using this. Right. These are all the bottles which we have already seen. This is the ether bottle with their markings. This is the lever to switch it open or close. This is the plunger to increase the vapor concentration. Here there is no specific concentration which can be measured. It is the lever position you can see in first position, second, third. There is no percentage. So they are all very unprecise or imprecise bottles. There is no temperature compensation. So these are all the. And can you identify this machine? Okay, this is called the Epstein Macintosh Oxford vaporizer, and this is a draw over concentration calibrated and flow over temperature compensated by Wagner jacket. Of course, this is a very specimen. Sometimes if you do extraordinarily well, they may ask you all these things. I'll just rub through. Now, what is a vaporizer? Define a vaporizer. Why should you use vaporizer?
It's a device that changes gas, liquid state to gaseous vapor state.
Very good. And does it deliver a precise concentration?
No, sir, we should adjust.
No. Nowadays, you are using 1%, 2%, 3%.
Yes, sir.
Every vaporizer, you have those numbers. What is that purpose for? To deliver
Yes,
the correct amount of gas. Okay? You don't imagine the old vaporizer which I showed. The modern vaporizers, they are all very precise. And they work at whatever temperature there, they are all temperature compensated. Which we will see how they are doing that. So vaporizer is a device that changes liquid anesthetic into vapor and adds the other gases to the fresh gas flow to the breathing system and deliver a precise concentration. Okay. So to understand about the working of a vaporizer, you need to know a few terms. Okay. One is called, what is the difference between a gas and vapor? I think we have discussed it in the last class. And again, I will show that later. And you must know what is saturated vapor pressure. And you must know the meaning of boiling point. Can you tell me what is the definition of boiling point from the previous slide I showed you? How do you define boiling point of a liquid?
Liquid becomes vapor at that point, sir.
Liquid becomes vapor at what?
Specific temperature where the vapor pressure equals the atmospheric pressure. So
Atmospheric pressure, exactly. So the
it changes
boiling
to
point
gas.
is the temperature. So if you say boiling point of water is 100, that means the vapor of water becomes equal to atmospheric pressure at 100. Okay? So any liquid, when it becomes a vapor and equals to the ambient pressure or atmospheric pressure, the temperature at which it happens is called the boiling point. Okay, that is a very important definition all of you should know. And formula to calculate the gas concentration. Of course, we will see that later. You must know what is splitting ratio. You must know what is variable bypass. You must know what is a measured flow. You must know what is latent heat of vaporization, and you must know specific heat and thermal conductivity. These are all the terminologies that you should be able to understand the vaporizer's function. So what is the difference between a gas and vapor? I think I told this in the last class. Can a gas be compressed into a liquid? The oxygen in your
No,
oxygen
sir.
cylinder
Mm.
which you are using in the machine, is it in a gaseous form or in a liquid form?
Liquid form, sir.
Oxygen
The oxygen, sir,
the cylinder that you are using in the machine, it's mounted in the machine, is it in the liquid form?
Gaseous
I'm
form.
not asking about the liquid oxygen tank that you have outside the hospital.
It's the gaseous form, sir.
Gaseous form. Whereas nitrous oxide,
liquid form, sir.
liquid form. Okay. So when a liquid becomes a vapor and it can be compressed again into a liquid, that is called the vapor. Okay. The gaseous form of a liquid which can be again compressed back to form a liquid is called a vapor. Gaseous form is a gas is one which cannot be compressed into a liquid at its critical temperature. Okay. The vapor is a gaseous form of a substance which is normally a liquid or solid at room temperature and becomes a vapor at a particular temperature. Gas is a substance that has no shape or volume and it is above the critical temperature of the agent. So for example, this is the oxygen and this is the above, which is above its critical temperature. You apply pressure, still it remains as molecules of gaseous oxygen only. Whereas a vapor, when you apply pressure, because it is below its critical temperature, you can see some of them have become a liquid here and some of them are still remaining as a gas. So it does not remain in the gaseous form all the time. So a vapor below its critical temperature can be compressed by applying pressure into make it into a liquid. And what is saturated vapor pressure? This is the second point that you have to understand.
Saturated. The vapor pressure of the liquid is saturated. I mean, the vapor pressure is exerted by the liquid to maintain an equilibrium with the system.
Or almost there, but little more proper explanation is required. As a liquid continues to evaporate into a space above it, the pressure it forms is called the vapor pressure. Okay, the pressure exerted by the evaporated portion of a liquid above its surface is called the vapor pressure. And as the evaporation increases, the vapor pressure also will go on increasing. But after a particular level, it becomes so fully saturated that it cannot become anymore into gaseous form. It cannot evaporate. So the equilibrium reached between the gaseous form as well as the liquid form is called the saturated vapor pressure. Okay, a point of equilibrium is reached at which the rate of evaporation equals that of condensation when the space becomes saturated. This is applicable to a gas or a vapor within a closed container. Okay, so this point where it is equilibrium with the solution is called the saturated vapor pressure. So for example, now here this picture shows the liquid is evaporating into gaseous form. But if it is a closed container, what happens after a particular time when the evaporation goes on happening, this pressure equals the pressure in the liquid also. Then no more gas can, no more liquid can evaporate. And that point is called the saturated vapor pressure. And this is a very important concept for the operation of any vaporizer. Okay. And the boiling point definition is, it is the temperature at which the vapor pressure of a liquid equals the ambient pressure surrounding the liquid. And what is the difference between evaporation and boiling? Now, if you keep a liquid open to atmosphere, any liquid will start gradually losing its volume because it starts evaporating. Especially if you keep a glass of water open to atmosphere, will it be the same volume the next day morning if you see?
No, sir.
It will not,
It will
it will slightly reduce because it gets evaporated. So what is the difference between simple evaporation and boiling? When will you get the hot water? என்ன ஒரு simple question வந்து 5 மணி மௌனிகமா இருக்குங்களேம்மா.
Evaporation can occur at
You require external heat for boiling, isn't it?
yes, sir.
So that you cannot do that. And it happens both from the inside of the liquid as well as the surface. Whereas evaporation happens only at the superficial layer.
Surface of
It will not happen from the bottom. Okay. So that is the difference between evaporation and boiling. How to calculate the vapor concentration using SVP and atmospheric pressure? It is a very important point. So for calculating the gas concentration, you must know the saturated vapor pressure of that liquid divided by the ambient pressure. For example, the saturated vapor pressure of sevoflurane is 20.1 bar, whereas the atmospheric pressure is 100 bar. So 20.1 divided by 100, you almost get 20%. That is the gas concentration. If you pour sevoflurane directly onto somebody's face, the percentage of sevoflurane you will get is 20% because the saturated vapor pressure of that is 20.1. And you are pouring it into an atmosphere where the pressure is 100, and that is the reason why you require a, and 20% sevoflurane if you pour on somebody's face, can the patient live?
No, sir.
It will cause severe cardiovascular respiratory collapse, and that is the reason why we use a vaporizer to deliver precise concentration. What is the maximum percentage you deliver to a patient and in your through your apparatus or vaporizer?
8%.
8%. It is the safe limit. Okay. So if you want to deliver 8% only maximum, you have to use a vaporizer. You cannot use sevoflurane, isoflurane, or desflurane like open drop what we used in the olden days. Okay. So this is a very important concept that you have to know. So how is the concentration or gas is expressed? It is expressed as the partial pressure or as volumes percent. Okay. So what we deliver in our machines are all concentrated as volumes percent, but the pressure, partial pressure is the correct way of doing it. So volumes percent expresses the relative ratio of the gas molecule in the mixture, whereas partial pressure expresses the absolute value. What is splitting ratio? Any idea? How do you get your sevoflurane when you switch on your vaporizer machine? Say after induction of anesthesia, you have intubated the patient, you are keeping say 1 liter of oxygen and 1 liter of medical air, and you want to maintain the anesthetic depth, so you open the sevoflurane, your assistant tells you keep it at 2%. So how is this 2% of sevoflurane delivered to the patient?
Sir, it's a proportion of fresh gas that's going into the vaporizer. Sir.
So the fresh gas flow, whatever is coming from the flow meter is called the fresh gas flow, because it is fresh because it does not have any other thing other than what you have proportionately kept in the flow meter. Okay, so that is called the fresh gas flow, and depending upon the percentage that you keep. Now when you keep 1 liter of oxygen and 1 liter of air, you get a total of 2 liters coming out per minute. Okay, the entire 2 liters, if you don't switch on the sevoflurane vaporizer, will directly come out to the breathing circuit. On the contrary, when you keep it at 2 liters, part of this 2 liters will go into the vaporizer, pick up the sevoflurane vapor and come and join the rest of the gases at the outlet and then come to the patient through the breathing circuit. So the higher the concentration you keep, more amount of fresh gas flow will come into the vaporizer to pick up the vapor and come out and increase the concentration. Okay, so this ratio which goes into the vaporizer and the part which does not go to the vaporizer and goes straight and mixes with the vaporized liquid at the outer end, that is called the splitting ratio. So the ratio between the portion of the fresh gas go entering the vaporizer and the portion that does not go into the vaporizer and travels straight through that is called the splitting ratio. Okay, so the ratio of bypass, that gas that straight goes without entering the vaporizer is called the bypass gas, and the gas through the vaporizer compartment is referred to as the splitting ratio. This splitting ratio will go on be increasing when you want a higher concentration, and it will be decreasing when you keep lower concentration, and it will be completely going through the bypass if the vaporizer is completely switched off. Okay, so that is the basic thing that we have to understand. So I am showing here, this is the fresh gas flow is coming from the flow meter. Okay, and this is the control dial, and this is the splitting valve which differ. So whatever gas is there, part of it is coming when the control dial is set at a particular level, and some of the gases are going straight. This is the bypass pathway. So the gas entering the vaporizer, they pick up this pink dots. They are all the anesthetic vapor. So they pick up that, and the blue arrows and blue dots are the fresh gas flow, and they mix here at the outlet. This is the inlet of the vaporizer, this is the outlet, and this go through the back bar to the patient. And so this is the picture to show the splitting ratio. So part of the going to the vaporizing chamber and part going through the bypass, the amount between these two is called the splitting ratio. Now, what is the latent heat of vaporization? These are all basic physics questions you would have studied in your +2. This is nothing new that we are learning. But because it's many years since you passed your MBBS, you have forgotten all your 12th standard physics, I suppose. What is the meaning of the word latent?
It's already inside.
Hidden.
Hidden.
Latent means hidden. Okay, the exact meaning of the word latent means hidden. And what is the opposite of latent?
Apparent.
Overt. It is overt. It means very exhibited. Apparent is not the correct word. Latent, overt. Okay. So the latent means hidden heat. Where is the heat hidden? For example, if a liquid is capable of becoming a vapor by evaporation, where does it get the heat to become a vapor?
Sir, that intermolecular attraction.
It has got a heat inside itself. Okay. So the latent heat of vapor, the amount of heat that is needed to convert a unit mass of liquid substance into gaseous phase at a constant temperature is called the latent heat of vaporization. So every liquid, when it is capable of becoming a vapor, it supplies its own heat because of, as you said, by the molecular collision. Okay, and if you apply external heat, it becomes boiling. Okay, so the heat that is generated and supplied for the liquid to form its own vapor, which is hidden inside, we don't see it outside. So that is why it is called the latent heat of vaporization. So every liquid has got a different level of temperature at which it will become a vapor. Some will become vapor very fast. Some will, for example, camphor, which is a solid. If you keep it in an open box, what will happen? After 2 or 3 days, will you see the camphor there?
No, sir.
No, because it has a high latent heat, it will automatically evaporate and become reduced. Whereas some liquids which have low heat, latent heat of vaporization, they will take a long time to become a vapor. Okay, so that is the thing that you have to. And what is specific heat? It is the amount of heat required to raise the temperature of a particular substance at what weight, at what to what temperature. That is the definition. So specific heat is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree centigrade. These are all basic definitions which all of you would have studied as standard students. These are all very applicable now because every liquid has got a different specific heat. Some liquid may require more heat, some liquids may require less heat, just like the latent heat. This is also very, very important. And the specific heat of a metal with which we make the vaporizer, that is also very important. And the thermal conductivity, this is applicable to the metal that we choose to make a vaporizer. What is thermal conductivity? It is the ability of the metal or material to conduct the heat. That's all. So thermal conductivity of a material is a measure of its ability to conduct the heat. So if a material, for example, copper and iron, if you both receive a heat, which will conduct heat faster? If you keep a copper vessel as well as the iron vessel and heat them up, which will get heated faster? No idea?
Yes, yes.
Copper will why so much of hesitation for that? Okay? Copper has conduct faster than iron. Okay, so variable bypass vaporizer is the one where you can have a total background flow and also it can split into two streams. Okay? So the bypass which can vary is called a variable bypass. Part of the flow can enter the vaporizer, part can go straight, or all of them can go straight. Okay, so that variation, if it is possible, it is called a variable bypass vaporizer. The smaller stream which acts as a carrier gas passes through the vaporizing chamber and the remainder gases go straight out of this chamber. Okay, and what is a measured flow vaporizer? So in some vaporizers, no fresh gas flow will enter the vaporizer. Instead of that, some other arrangement is made to evaporate the liquid and then the vapor of that liquid is injected into the fresh gas flow through another separate channel. That is called the measured flow vaporizer. Which vaporizer is working like that in the modern day?
X6.
Desflurane. Okay. So measured flow vaporizers have a separate independent stream of vapor carrying gas that is added to the fresh flow to deliver an accurate agent concentration. The vaporizer must measure and adjust for the fresh gas flow rate. Okay. So example is here. So these are all the saturated vapor pressures of various anesthetic agents. Ether 59, halothane 32, and fluorine 33. Desflurane has the highest saturated vapor pressure, and that is the reason why it cannot be used in the normal vaporizer that like your sevoflurane. Sevoflurane 21, isoflurane 33. And what will be the concentration of the agent shown here if used in open drop method at sea level? Using the formula that I showed you in the previous slide. Supposing ether, if I use, what will be the percentage of ether? SVP divided by ambient pressure or atmospheric pressure multiplied by 100. Okay. So the same number will become the percentage. It will become 59% ether. It will become 88% sevoflurane. It will become 32% halothane. It will become 21% sevoflurane. The formula I told you, that is the reason why I told you the formula first. Okay. So it will be ether 59, halothane 32, the same number you will have to say as percentage. Is it clear or not? Are you all able to understand? Or shall I close the class? It is becoming getting too tedious for you.
Uh, can you explain that formula again, sir?
SVP, saturated vapor pressure divided by atmospheric pressure multiplied by 100. Atmospheric pressure is 100 bars.
Okay, sir.
Saturated vapor pressure is 21 bars. So 21 by 100 into 100. So the same
Okay, sir.
number will become percentage. கணக்குல அவ்வளவு வீக்கா நீங்களா?
No, sir.
Is it not very easy? 59
Yes, sir.
divided by 100 into 100.
Into 100. Yes.
32 divided by 100 into 100. 88.5 divided by 100 into 100. Okay. So that
Okay,
is
sir.
why all the modern agents, you cannot use them as open drop. Whereas ether, even at it is at 59%, it is still safe because it cannot cause that much of a depression like your modern agents. So we cannot use any of the modern agents by open drop method. In the first slide, what I showed you, but ether can still be used. Why ether is the only agent to be used by ether drop? It's a safety margin, large gap between therapeutic dose and lethal dose. And average anesthetists with average skill cannot kill a patient with ether. That is the adage that we used to follow. Okay. So how are vaporizers classified? Any idea? You all go through any
Variable bypass,
Ah,
measured flow and variable bypass, and measured vaporizers, variable bypass vaporizers.
okay, very good, very good. There are 6 points to be included. Okay, so one by one I'll tell you. Vaporization method, that is when the fresh gas flow enters the vaporizing chamber, it can just carry the vapors that are present on the superficial part of the liquid, surface of the liquid. Then it is called the flow over type. It just flows over the surface and carries whatever vapor has been already formed. In the older machine, which I showed you, the ether bottle and trilene bottle, there is a rod which can be pressed. Then what will happen? All the gases will go under the surface of the liquid. When they go under the surface, they will form bubbles. And that bubble, each bubble will have a larger surface area to carry more vapor. So if you want to increase the concentration, you can blow the fresh gas into the liquid depth and form bubbles to carry more. Okay, that's called the bubble through. And with or without the wick or the other extra surfaces to make more vapor. So that is the first method of classifying depending upon the vaporization. Second is regulation of output. That case can be by, as you said, variable bypass or measured flow. Then the third point is temperature compensation. In the older boil machine, the ether and trilene, they don't have temperature compensation. They take the heat from the surrounding atmospheric air. It is conducted through the bottle and then the liquid gets vaporized. Whereas in our new machines, we have methods to adjust to the temperature. If the temperature drops, then automatically vaporization will come down, concentration will come down. To prevent that, they will allow more fresh gas to come in. On the contrary, if the temperature increases, then to prevent excess vapor formation, they will automatically reduce the fresh gas flow even though you are setting it at a different level to adjust and deliver the correct concentration that is required. So that is called the temperature compensation, which is present in most of the vaporizers, and that is why the modern vaporizers are called, what is the name given to the modern vaporizers? All these sevoflurane, isoflurane, desflurane.
Tech vaporizer.
TEC vaporizer, TEC. TEC means temperature compensated. So that is the short form for this TEC vaporizer. And then agent specific or multiple agents. So in the older machines, you can pour ether into ether bottle or into trilene bottle and also use it. Whereas here, if you are using a sevoflurane, you have to use only sevoflurane in that vaporizer. You cannot pour isoflurane or enflurane or halogen. Whereas there are now vaporizers coming with facility to use multiple agents. Can you tell me an example of vaporizer which you can use with multiple agents? Okay, try to think over and tell me. Then the fifth category is what is called the plenum vaporizer and draw over vaporizer. Draw over vaporizer is the one which normally attributed to the boil bottle or trilene bottle, where the fresh gas flow will come, pick up the vapor on the surface and go. But plenum means injecting the fresh gas flow with pressure. That is called the plenum vaporizer, and all the modern vaporizers which now we use, they are all plenum vaporizers, because at the inlet of the vaporizer, the gas flows into with a pressure. So they are called plenum vaporizers. And whether the vaporizer is located within the circuit or within the breathing circuit or outside the breathing circuit, nowadays all our vaporizers are outside the circuit only. Earlier, we used to use the vaporizer within the inspiratory limb and the expiratory limb of the circle system. Then it was called vaporizer inside the circuit. We don't use it anymore nowadays, and so all our vaporizers are outside the breathing circuit. So vaporizer outside the circuit is fixed. So these are all the 6 categories which have to be included if you want to describe a vaporizer. So give examples based on this classification. So these are all the methods of vaporization. You have flow over, you have bubble through, you have injection. So injection is desflurane, bubble through is copper kettle and your boil bottle, and flow over with or without wick is Goldman, etc., which most of you would not have seen. Method of regulating output, variable bypass, you have the TEC vaporizers. Measured flow, you have again copper kettle and your desflurane. Location, inside the circuit, you can use the old Goldman vaporizer as well as the Oxford miniature vaporizers. Outside, most of the TEC vaporizers we use only outside. Temperature compensation by altered flow, by supplied heat or both. And agent specific, you have TEC vaporizers, and multiple agent, you have Goldman bottle. And resistance, you have plenum, high pressure, and draw over. So all the 6 have been described, and the vaporizers examples are also given. So what is the difference between plenum and draw over? In plenum, fresh gas enters the vaporizer at a pressure. In draw over, fresh gas flows over the surface of the liquid at normal pressure. And based on this classification, whenever you want to describe a vaporizer, how you should describe? You should say concentration calibrated, plenum type with variable bypass, flow over with wicks, temperature compensated, out of circuit, and agent specific. So whenever a description will be given, you must include all the 6 features of the vaporizers to describe that. This is how the vaporizer should be described. What is the difference between boiling and evaporation? Already we have seen. In boiling, you require external heat. Evaporation occurs accidentally. Vapor pressure, again, we have seen that. What is the significance of vapor pressure? It helps to predict the boiling points, create phase diagrams, and determine chemical stability. Okay, so that is the importance also of vapor pressure. So what is critical temperature? It's the maximum temperature at which a substance can be converted from gas to liquid by compressing it. Okay, that is the definition of critical temperature. Boiling point, again, it is the temperature at which the vapor pressure equals the ambient pressure. The saturated vapor pressure, mentioned the vapor pressure alone is not sufficient. So vapor pressure increases with increasing temperature. So saturated vapor pressure is the vapor pressure of the agent mentioned along with the temperature. So this is the most important factor in an anesthetic agent that decides the vapor design. So already I have shown you part of the gas is going straight, part is coming out. This is called the variable bypass vaporizer. Now this is adding by injection. So what should this be called? You know, fresh gas flow is coming separately in a tube and the vapor is formed separately and then it is added to the fresh gas flow by another separate tube. This is called the, what I showed you earlier, measured flow. Okay, measured flow vaporizer. And this is the difference. So in measured flow, no fresh gas enters the vaporizer. The vapor is injected in measured quantity to the fresh gas passing through the separate tube. So how is the vapor concentration achieved in measured flow vaporizer? That is the mechanism of working of desflurane vaporizer. Okay? The variable resistance controlled by the anesthetist adjusting the dial of the vaporizer, and the differential pressure transducer is present. Because if you see a picture of that interior of the desflurane, you will understand that better. And in between the fresh gas line and the vapor line to help achieve the controls correctly. This is a variable control at variable settings to understand how it works. So you can see when the control dial is at 0, no flow is happening. All the gases are flowing through the bypass pathway. Not a single molecule of gas is going through the vaporizer. But as you set different dial setting, the volume of gas going into the vaporizing chamber increases. And I hope this will give you a good idea about what is the variable flow at various temperature. Why selection of a metal with good thermal conductivity is important in making a vaporizer? Okay. Can you just think logically and tell me what is the reason why you have to have a metal with a good conductor?
No idea.
And only supply the heat. Okay.
Heat
Temperature decrease, temperature in vapor. So if the temperature of the liquid drops, the vaporization also will come down. Okay. So if you have a metal which can deliver heat from outside with a good conductivity, then vaporization will be helpful. Okay. So if a metal which retains heat, that also will help to vaporize. And metal which donates heat. So metal can conduct heat well, it can retain heat, or it can donate heat. From all these three aspects, the metal out of which we make the vaporizer is very, very important for maintaining the vaporization. Okay. What are the effects of circuit back pressure on vaporizer? This is the pumping effect and pressurizing effect. I think all these things need a little bit more of detailed explanation. I don't know how many of you are fresh enough to. Shall I continue or stop here? Because this is a very common question asked in the exam.
Sir, we can continue, sir. We can continue.
Continue. Okay. Right. Now let us practically see. Every day you are anesthetizing a patient. You are paralyzing them. You are taking over the respiration and you are giving positive pressure ventilation. Okay. Now when you squeeze the bag or the ventilator squeezes the bellows to put the gas into that, will all the gas only go to the patient or part of it can it go back into the machine?
Sir, the scavenging system also, sir. Part of it
The
go back.
scavenging system is there to eliminate whatever is still out. We are not,
Can
that
go
is
back.
not directly directed.
It can go back, sir. It can go back.
So So it can go back into the circuit and prevent the fresh gas flow coming. It can form some sort of obstruction to the fresh gas flow, isn't it? That is what is called the pressurizing effect. Okay. When the pressure is positive pressure is given to the breathing circuit, it will not only transmit the pressure towards the patient's lung, but part of the pressure will go in the reverse direction to prevent the fresh gas flow from coming out of the machine. Okay, this is the first basic fundamental point that you have to understand. Now, when the reverse flow occurs and prevents the fresh gas flow coming back, entering into the breathing circuit, what can it produce? Where is this fresh gas flow coming now? It is coming out of the vaporizer. Okay, if the vaporizer is on, part of the gases are going for the bypass, part of the gases are going into the vaporizer and coming and trying to enter the fresh gas flow. So at the outlet of the pressure vaporizer, what is the effect that this back pressure produces is what we have to understand. And that is what is called the pumping effect and pressurizing effect, which is also called the hill and low effect and pole effect. Okay. Now, what are the changes that happen during generation of positive pressure? When the bag is squeezed, pressure in the breathing system increases. This pressure is transmitted back into both the bypass channel, also to the vaporizing chamber. Part of it goes straight to the patient. The fresh gas tries to move forward and gets compressed by the bypass channel and vaporizing chamber. Okay. During sudden release of this, after inspiratory attempt, when you release allow the expiration to happen, what happened? When the positive pressure is released, expiration, previously compressed gases now suddenly expand in all directions. And some of them rapidly expanding to enter into the inlet of the vaporizer and cross over into the bypass channel to cause excessive carrying of the vapor. So the final output concentration, normally a vaporizer's bypass channel does not have vapor, but so this vapor due to the pumping effect is additional. So bypass you have to have a pure fresh gas flow normally. But this pumping effect, what does it produce? It makes some vapor flow like a leak into the bypass chamber. And when this bypass vapor flows across to the exit, it meets the vapor coming from the vaporizing chamber, and both of them produce an excess of or increased concentration than what you set in the vaporizing dial. So I will show you with this picture pumping effect or back pressure effect. Now the bag is squeezed either by you or by the ventilator. So there is a forward pressure as well as the backward pressure. Okay, so the backward pressure goes to the outlet of the vaporizer, and this pressure travels through the bypass chamber also. And then what happens? It pushes more fresh gas flow than what is required into the vaporizing chamber. And the next step, the bypass chamber has pushed more gases into the vaporizing chamber, and the bag is now relaxed during expiration. So whatever excess gas has entered the vaporizing chamber, that also carries vapor and comes into the outlet. And so ultimately what happens? The gases which are coming more than what is required, they increase the higher concentration. So for example, if you set the dial of the sevoflurane vaporizer at 2%, and if this pumping effect is taking effect like this, you will deliver 2.5 or 3% instead of 2%. Okay, so that is the mechanism of what is called the pumping effect. Are you able to understand this? Is it clear?
Yes, sir. Yes, sir. Yes, sir.
Okay, so remember this back pressure causes some of the fresh gas flow to enter because of it is not allowing the bypass gas to go straight. Some of them take the route, enter into the vaporizing chamber and carry more vapor and come out and increase the concentration. Now the next effect is what is called what are the methods of preventing this? But in modern vaporizers, we don't allow this pumping effect to happen. We don't want when you said 2% and you keep on giving 3%, your patient will be deep and there will be delay in recovery. So we don't want that to happen. So there are methods of reducing this pumping effect is, one is make the inlet tube longer so that whenever there is a back pressure, the fresh gas flow will travel towards the flow meter and not enter the vaporizing chamber. So that is the first alteration that you can do. Have a long inlet tube, then increase the resistance to the flow. That is, if the back pressure is coming, you put a valve and don't allow that back pressure to reach the bypass chamber or the vaporizing outlet. Okay, so that valve will prevent the back pressure going. That also will prevent the so open one way when there is a forward flow, that will not allow the backward pressure to go, and so closed valve. So these are the two methods of or three methods rather. One is to have a long inlet tube. Second is to increase the resistance at the outlet. And third is to have a one-way valve which will prevent the backward pressure getting transmitted to the bypass chamber. Okay? By these methods, we can reduce the pumping effect and thereby maintain the correct concentration which is set on the dial. I hope it is clear for all of you.
Yes, sir.
Okay. So can isoflurane be used by open drop method? The answer is no. Why? Again, this is a question based on the SVP that I showed you earlier. Okay. So the saturated vapor pressure is 241 millimeters of mercury or 24.1 atmosphere. So 760 millimeters. So roughly it is about 33%. So that is a very dangerous percentage. So the function of vaporizer is to deliver the correct concentration. So this one gas and vapor again. Methods to increase the vaporization is fresh gas flow picks up vapor from the vaporizing chamber. So if you keep a higher flow, will it pick up more vapor or less vapor? For example,
higher.
you use a fresh gas flow of 2 liters oxygen and 4 liters nitrous oxide and set the sevoflurane dial at 2%. Will it pick up more vapor or less vapor?
Sir, more vapor.
Logically thinking, it looks like that. But when you
Yes.
have a higher fresh gas flow, it has lesser time to travel. Okay.
Okay.
So it
Yes, sir.
requires some time for the gas to pick up the vapor. So if you have a higher gas flow, what will happen? It will travel faster and so it will pick up less vapor. Whereas if you have a low fresh gas flow, it is only in the uncompensated or the older method where you can use a higher flow to pick up more vapor from the surface. But in the modern vaporizer, the higher flow will pick up lesser quantity of vapor, lower flow will pick up more quantity of vapor because there is more time for the gases to travel through the vaporizing chamber, and that is how you will end up with the difference. And these are the wicks which increase the surface area. So if you want more vaporization to happen, you can use these wicks to carry. The wicks will have capillary action and they will suck the liquid anesthetic agent and spread them over an area like this. And when gases travel through that, they pick up more vapor. That is the mechanism of wicks. Or you can use the bubble through. So gas can be delivered into the depth of the liquid and that will form bubbles and each bubble will have excessive surface area and they can also pick up the vapor. Okay? So the pressurizing effect is one which is a opposite of pumping effect. Okay? In pressurizing effect, what happens? The output of the vaporizers decreases when there is a back pressure. This effect is greater when the high flow rates and large pressure fluctuations and low vaporizing settings. The change in vaporizer output caused by pumping effect is usually greater in magnitude than those associated with the pressurizing effect. And pressurizing effect with a high gas flow causes decrease in pressure. Pumping effect with low gas flow is more important because it will increase the concentration. So that is the picture to show how the pressurizing effect works. Increase in pressure is applied to the vaporizing outlet here. Just like in pumping effect, pressurizing effect also produces a backward pressure on the vapor outlet and compress the carrier gas so that there will be more molecules per ml. The number of anesthetic vapor molecules will not increase as this depends on the vapor pressure of the anesthetic. So the net effect is a decrease in the concentration of the anesthetic delivered. So what you have to remember and the answer in the exam is pumping effect without any compensatory mechanisms like I told you with a longer inlet, with a resistance or with a one-way valve will develop or will produce increase in concentration. Pumping effect increases the concentration. On the contrary, pressurizing effect is supposed to reduce the concentration. Whether you understand the detailed mechanism or not, this is the answer that you have to give in the exam. Pumping effect increases the concentration delivered by the vaporizer. Pressurizing effect decreases the concentration produced by the vaporizer. So this is the picture and this is the capital letter, big bold letter writing that is happening. So this, if you remember that much is enough. And what are the methods of temperature compensation? That is ambient temperature and temperature of the liquid, all these things can vary, but to deliver the set concentration, you have so many methods. One is called the metal rod method. So this is a rod which is guarding the inlet to the vaporizing chamber part of it. So fresh gas flow is split into bypass gas flow and the gas that has to flow into the vaporizing chamber. And always remember that increase in temperature increases the vaporization, decrease in temperature decreases the vaporization. So if there is an increase in temperature, decrease in temperature, what will happen? It will let out more fresh gas flow to pick up more vapor. Okay? And that will, I mean, this is increasing temperature. So this outlet is blocked partially. So the amount of fresh gas flow entering comes down. There is a decrease in temperature. This outlet opens out more. I mean, the inlet opening is guarded, which is reduced, and more fresh gas flow comes in. Okay? This is a simple picture with which you can understand. Increasing temperature, decreasing fresh gas flow. Decrease in temperature, increasing fresh gas flow by the metallic guard that is available at the inlet of the vaporizing chamber. Then they have changed this into some sort of bellows-like thing with a blocker at the inlet. So again, increase in temperature, the bellows will expand and the inlet entry will be partially blocked. And if there is a drop in temperature, the bellows will shrink and the entry point will open and more gas will come inside. But the commonest method used is what is called the bimetallic strip, which is available. So there are two metals which are clubbed together, which have different thermal expansion quality. Okay, so when there is, this is the normal position. When there is a low temperature, I mean high temperature, both of them expand like this. When there is a low temperature, both of them shrink like this. Okay. Now imagine that both of them are coupled together. So they are called bimetallic strip. So at high temperature, what happens? Both of them expand and go and try to occlude the inlet opening into the vaporizing chamber. At low temperature, they shrink and naturally open up the inlet so to allow more gas flow. So you can see this. This is the bimetallic strip. This is the blocker to allow the the controlling the entry of gas into the vaporizing chamber. So when the temperature is high, it stretches and occludes this opening partially so reduced fresh gas flow. When the temperature is low, it bends backward, opens out, more fresh gas flow is coming. You can see by the blue arrows. So high temperature, lesser flow, low temperature, greater flow. Very simple to understand. So this is how the temperature compensation is done in all the modern vaporizers, so that the delivered concentration and the dial set concentration are both remain equal without any fluctuation. Okay. So another important law which is very useful in this is the Dalton's law of partial pressure. So the total pressure exerted by gas mixture is dependent on the partial pressure of individual gases in the mixture. So explaining this in the atmospheric air, Pn plus, that is nitrogen plus oxygen, forms the total mixture, and this is the various percentage. We have 78% nitrogen and 20% oxygen plus the other gases. They make total of 760. Whereas volume percent is number of units of volume of gas in relation to the total of 100 units of volume. So it expresses as the relative ratio of gas molecule in the mixture. So volume percent is calculated by volume occupied by the gas by total volume multiplied by 100. And partial pressure of a gas divided by total pressure into 100 also gives you the concentration. So if there is an altered barometric pressure, like for example, if you go to a hill station and where there is a, normally at higher altitude, what will be the barometric pressure? Same or reduced? No answer at all. Are they all there or not?
Reduced.
Actually, at the higher altitude, the barometric pressure, atmospheric pressure is reduced. Okay. So if you go to high altitude, if you keep a normal dial setting and sea level pressure is 760, whereas the ambient pressure at the higher level is, for example, it is 630, then you will have 760 divided by 630, you will have same isoflurane set at 1% at sea level will deliver 1.2% at a higher level. Okay. So the delivered concentration will be higher, but partial pressure will not be increased. That is a very important thing. So you set a concentration of 1%, but at a lower atmospheric pressure at high altitude, the delivered concentration becomes 1.2. But the partial pressure, if you calculate, 1% of at sea level is 7.6, and 1.2% at 630 millimeters is also 7.6. So the partial pressure will remain same, but the delivered concentration will be higher. And the question they ask you in the examination, will you have to calibrate your vaporizer for usage at a higher atmospheric, lower atmospheric pressure at high altitude situations? The answer is no. Even though the delivered concentration will be higher, the partial pressure remains the same. So there is no need to calibrate the vaporizer at a higher altitude where the ambient temperature will be low. Okay. And these are all the various types of vaporizers which you see. This is the Tech 5, this is the Tech 7, and this is the Vapor 2, and this is Sigma Delta companies. And they are all working on the Selecta Tech mounting system. And these are all some of the old type of vaporizers which sometimes the examiners are fond of asking. So I'm just showing the very model. This is the Tech 2 vaporizer. You can see the dial is projecting like this in the front, not like on the top. Okay? And the filling system. And what is this portion in all this? What is this called in the vaporizer? What do you see through this glass?
Whether the liquid anesthetic agent is full or not, how much the level of
The level of the anesthetic agent. Okay, the liquid anesthetic agent when you fill. And what is the name for this? This is called the sighting glass. Sightting. This is the sighting. You look through this to see the level of the glass. So this is called the sighting glass. So the models, the filling system is different here. This filling system is different here. So this is the Tech 2 vaporizer where the dial was like this. Then they made it to top dial level with a press. There's a lock for this. You have to press this to rotate. This is Tech 3 for halothane. Then this is the again Tech 3 for isoflurane. This is called the Somni 3 funnel fill vaporizer for isoflurane and sevoflurane. And these are all some of the methods of filling the vaporizers, which they also ask you. This is called the pour fill, old method. You have to just remove the cap and then pour the liquid directly onto that. This is called the key fill, where you have to fix this key and then insert that into that to fill. This is called the quick fill, which many of you may be using in your regular paper. And this, what is this called? This is called the Aladdin vaporizer. Okay? So this is an Aladdin cassette vaporizer, and the cassette vaporizers regulate anesthetic vapor concentration, the electro-pneumatic proportion, flow valves control microprocessor. So this is a computerized or microprocessor operating. So different cassettes with color coding are there. This is the handle, and you have to insert it into the slot that is will be there in the machine. This is the filling port. You remove the cap and fill that, and you can see the level of the liquid in this sighting glasses here. And then just you have to insert that instead of fixing it like your back bar, which is inserted. And then this is the various parts of that. The difference between these two cassettes are, one is the top is easy fill or quick fill, and the bottom is key fill type. And the Aladdin cassette vaporizer is sometimes asked as a short nose. It consists of two parts, an electronic control mechanism and a portable cassette. Okay? The electronic control mechanism is in the anesthesia machine, and the agent is in a portable cassette that is inserted into the slot in anesthesia machine, which recognizes the contents of the cassette and dispenses agent into the stream into fresh gas flow. And each cassette is a liquid sump with control mechanism and can be tipped and it's maintenance free. It cannot deliver volatile agent in the absence of main power or battery backup and adequate oxygen pressure. And it's functionally similar to the conventional vaporizers with bypass chamber and vaporizing chamber. The maximum volume of agent that it can hold and volume that in the ball of sight is in the bottom. It holds 250 ml when it is full. When the ball in the side tube is at the bottom, it still has 80 ml or less. Safety features of Aladdin cassette vaporizer: when only 10% of the liquid remains in the cassette, an alarm message appears. The fresh gas in and out of the cassette is electronically measured for enhanced control. And when cassette is removed, two spring-loaded valves automatically close the channels to and from the vaporizer. The error situations, valves operate to cut off anesthetic agent delivery. And the pressure relief opens to the scavenging line if high pressure is detected in the cassette or the liquid level valve measuring device detected is overfilling. All these are advantages. This is the desflurane. All of you have seen this? Yes or no?
Yes, sir.
Why don't you immediately answer that? At least this is the construction of that desflurane. How see the fresh gas flow is coming through this, and this is the chamber separately vaporizing this, and these are all the pressure transducing valves. So there is a control here, and there is a pressure transducer which is sensing the flow of gases, and that only depends on, the dial setting. When you do that, it allows the vapor to directly come into that. So you can see that no fresh gas flow flowing from the flow meter anywhere entering this chamber. So vapor is separately produced and then injected into that which comes out. So this is another picture of the fresh gas flow coming from the flow meter going straight like that. This is the vaporizing chamber of desflurane. So with the heat, it requires heat to vaporize that. And so that is why it requires the electrical connection to operate. It cannot work if there is no power supply. And that will make the vapor to happen. And this differential pressure transducer will find out what is the pressure according to the flow rate that you keep and the dial setting here. Both will be balanced and the amount of vapor required will be injected into the gas flow. Okay. So it requires a different type of vaporizer. These are all the various parts. Number one is the flow meter, fresh gas flow. Fresh gas flow falling. This is the 2 is the pipeline through which it goes. 3 is the vaporizing chamber, and so this is the vaporizing chamber with the heating element. 4 is the vapor that is formed, and 5 travels through this line, and 6 and 13 are the two resistors, 2 valves that are there, and 12 is the computer. The vaporizer has the brain. It is able to alter the flow of desflurane by controlling the valve number 13, and desflurane goes through the pipe number 7, and it meets the fresh gas flow at the 0.8, and final concentration is delivered at 9. So this is a picture to show all the parts of that and understand how it is working. So flow in pipe 2 has a fixed resistance at 10 in its path, and 11 is called the differential pressure transducer. So this is the differential pressure transducer. All these parts, if you go through at leisure, you will be able to understand how it is working. And the safety advantages of tech vaporizers, they have interlock to isolate vaporizers when not in use, a clear indication of the liquid level through the sighting glass, a non-spill reservoir where up to 180 degrees if you fill, nothing will go out, and a keyed fill or a pore fill system prevent filling with an incorrect volatile agent and minimize the leaks, and increase wick capacity to increase the vaporization. How to calculate the volume of liquid agent used? For that, there is a formula called Ehrenwerth and Eisencraft, where you multiply set dial percentage with fresh gas flow in liters per minute multiplied by 3. You will get the volume of liquid that you use per hour. So 2% sevoflurane. If you use a fresh gas flow of 2 liters and you multiply by 3, then the total volume you will be using for an hour will be 12 ml of sevoflurane. This formula also they ask you in the examination. So higher the percentage, higher the flow rate, higher will be the utilization of that. Okay. So percentage multiplied by fresh gas flow multiplied by 3, you get the total volume used per hour of any volatile anesthetic agent. How to calculate the amount of vapor from 1 ml of volatile agent? That you have to use what is called the Avogadro's hypothesis. So 22,400 into density of the agent by molecular weight. For example, sevoflurane 22,400 divided by density is 1.5 and molecular weight is 200. So you will get 171 ml per ml of your anesthetic agent. Vapor will be 171 ml. So this is again the 6 mechanism. These are the safety features we already seen. The hazards of the modern vaporizers are tipping, overfilling, and leaks. These are the hazards that you have to know. Interlocking, how it works, you have 2 rods projecting like this. Okay? So when you fix that, one rod will lock the other one and will not allow it to go into on or off position. And identifying the filling vaporizer. So this is, I don't know how many of you have seen, this is how you unscrew and remove the cap. So any agent, if you this filling method by pouring, any agent can be poured resulting in the wrong agent. Filling, while filling can happen, and vaporizer need to be in off position if done during use. Whereas the other method, we can keep it in on position. This is the key filling, color coded pin for key filling for halothane and isoflurane. This is the cap, especially cap for filling for isoflurane. And the name of the agent for pin safety is called the Fraser-Sweatman pin safety, which I showed you in the earlier slide. And it has a component of this feed bottle collar adapted. So this is the filling only when vaporizer is off. And this is the way you have to insert. Mechanism of how it is done. These things are all known to you. The meaning of cleaner means full. So in air conditioning terminology, it applies to air that is forced in and cleaned and temperature adjusted. So cleaner vaporizers are designed for use with continuous flow of pressurized gas and have a high internal resistance. And this is how the cleaner vaporizers work. This is a copper kettle, world's first vaporizer. And, this is again a measured flow. Long before desflurane was now used, they have used this copper kettle as a measured flow. So this is a comparison between the two, the older copper kettle and the modern desflurane. And the difference between Tech 2 and Tech 3, these are all the questions examiners used to ask in the earlier time. So this is the main thing, dial position and filling method, and the metal, all these things are little different here. I don't think they'll ask you all that now. Tech 4 vaporizers, they are the different. Tech 5 features are they are variable bypass, flow over, out of system, temperature compensated, concentration calibrated, agent specific. Just like the 6 description I told you in the beginning that you have to use for all these various vaporizers also. So different models of the same vaporizer, desflurane by different companies. One is by GE Health, this is by Daiger and Penlon, and these are the easy fill methods of description. And this is the Aladdin cassette vaporizer parts. And this is the easy fill for CO-fluorine. And again, color coded Aladdin cassettes for ISO, CO, and desflurane. Yeah, this is the method of inserting the Aladdin cassette into the machine. So whatever machine has got this type, you have to just press it inside and then remove it. By pressing a lock, you can remove. By just pushing it, inserting and pressing, you can insert the cassette. So these are all the differences between the various types of cassettes. And there is another method called DIVA, direct injection of volatile anesthetic agent. This anesthetic vaporizer is a measured flow vaporizer, can be used for all models of anesthesia for desflurane. It has two sections, a plug-in for vaporizing module, which is a specific particular agent module, and the anesthesia machine. So these are all the pictures of how it is used. And this is the unit of DIVA which is being used. The hazards of using vaporizers, of course, already we have seen that overfilling, leak, and other things. Electronic failure in cases if it is an electronic control. Now, can anyone identify this? Somebody said the name in the beginning of the class.
Anaconda vaporizer.
Anaconda vaporizer, very good. So this is the anaconda vaporizer, where it is used mostly in ICU for sedation nowadays. Instead of using your parenteral sedative agents for patients on ventilator, they have used this. So patient is intubated, is in mechanical ventilation. So volatile anesthetic agent is filled in that, and it is being reused by the rebreathing. Okay, so that is the anaconda vaporizer. It is a miniature anesthetic vaporizer and the HME filter combined together. It is a combination of both. The device is meant to be used mainly for sedation in the intensive care and outside operating rooms. It is designed to deliver only isoflurane and sevoflurane, available presently in two different internal volumes of 150 ml to be used in patients with high and low tidal volumes. And so these are all the various vaporizers which you have to be aware of, and I hope you are able to retain at least part of what has been taught today, because these are all little dry subjects which you have to keep reading again and again to remember. And I hope at least now you have got some idea about how to use them in your day-to-day practice. Any doubts or any questions?
No, sir.
All out of what? Right. Well,